Welcome to a journey beyond the stars, where the mysteries of the cosmos come alive. Tonight, as you lay back and let your mind wander, we'll explore the vast expanse of space. A realm filled with wonders that stretch beyond our imagination. From the birth of the universe to the swirling dance of distant galaxies and the secrets hidden in the icy tails of comets, every corner of the cosmos has a story to tell. This isn't just a lesson in science. It's an invitation to marvel at the universe and let its beauty guide you into a peaceful sleep. So, dim the lights, breathe deeply, and let the magic of the universe lull you into tranquility. Let's begin this voyage among the stars. Please like and subscribe to our channel to stay updated with our latest and most exciting videos. Chapter 1. Asteroids. Asteroids are not just remnants of a chaotic past, they're cosmic storytellers. These rocky fragments hold clues to the birth and evolution of the solar system. Their diversity, from metallic giants to icy wanderers, tells us about the conditions in different parts of the solar system billions of years ago. Imagine holding a piece of an asteroid in your hand. It's like holding a time capsule from the dawn of our cosmic neighborhood. The asteroid belt, situated between Mars and Jupiter, is a chaotic graveyard of failed planet building. While Earth and its rocky siblings successfully formed, this region became a collision zone, thanks to Jupiter's massive gravitational pull. Jupiter's influence disrupted the delicate dance of rock and dust, causing fragments to crash into each other violently. Instead of forming a planet, these fragments remain locked in an endless cosmic standoff, orbiting the Sun as the asteroid belt. But the asteroid belt isn't the only place where these rocky relics exist. Asteroids can be found throughout the solar system. Some stray close to Earth, becoming near-Earth objects, NEOs, while others venture far beyond Neptune in the Kuiper Belt. These distant wanderers remind us that the solar system is not a static place. It's a dynamic, ever-changing realm. Some asteroids are metallic, rich in iron and nickel, while others are carbon-rich or icy. This variety hints at their origins. Some formed closer to the Sun, where it was hotter, while others came from the cold outer reaches of the solar system. This makes asteroids a treasure trove for scientists. By studying them, we learn not only about our own solar system, but also about how planetary systems form elsewhere in the universe. Asteroids aren't just scientific curiosities. They're also a potential resource for humanity. Mining asteroids could provide materials like metals and water that are essential for space exploration. Water from asteroids could be turned into fuel, supporting missions to Mars or even beyond. This vision of asteroid mining could one day turn these ancient rocks into stepping stones for humanity's expansion into the cosmos. But asteroids also pose a danger. Their orbits can bring them perilously close to Earth. Throughout history, asteroid impacts have shaped our planet dramatically. 66 million years ago, a massive asteroid struck Earth near modern-day Mexico, causing a catastrophic extinction event that wiped out the dinosaurs. This impact left a crater over 90 miles wide and sent shockwaves through the planet. It's a stark reminder that, while we owe our existence to asteroids, they also hold the power to destroy. Today, astronomers are constantly on the lookout for asteroids that could threaten Earth. Programs like NASA's Planetary Defense Coordination Office track thousands of NEOs, ensuring that any potential threats are detected early. Scientists are even developing ways to deflect dangerous asteroids. For example, NASA's DART mission recently tested a method to nudge an asteroid off course by crashing a spacecraft into it. This groundbreaking experiment proves that we can protect our planet from these cosmic wanderers. Despite their dangers, asteroids remain objects of wonder. Some are so large they have their own moons, like the asteroid Ida and its tiny companion, Dactyl. Others are shaped like potatoes, peanuts, or even dog bones, showcasing the strange and varied nature of these ancient objects. And then there are the icy asteroids, or comets, which leave bright glowing tails as they pass close to the sun, creating some of the most spectacular sights in the night sky. Beyond our solar system, distant stars host their own asteroid belts. These belts are like cosmic fingerprints, revealing the history of their planetary systems. For instance, the star Epsilon Eridani, just 10 light-years away, has not one but 2 asteroid belts. If we lived on a planet in that system, the belts would create a glowing streak in the night sky, far brighter than the Milky Way. Asteroids also inspire big questions. Are they carriers of life's building blocks? Some scientists believe that asteroids may have delivered water and organic molecules to Earth billions of years ago, setting the stage for life to emerge. If that's true, then these seemingly lifeless rocks might have played a key role in creating the conditions that made our planet so special. As we gaze into the future, asteroids hold the promise of discovery and adventure. Missions like OSIRIS-REx and Hayabusa, too, have already brought back samples from asteroids, giving us a glimpse into their ancient secrets. These missions are just the beginning. In the coming decades, we could see asteroid mining, planetary defense systems, and even human colonies that rely on asteroid resources. The story of asteroids is, in many ways, the story of us. From the swirling dust that formed our planet to the catastrophic impacts that reshaped it, asteroids have been both creators and destroyers. They remind us of our place in the universe, tiny beings on a rocky planet, orbiting a star, in a galaxy filled with countless stars, each with their own stories to tell. As we journey deeper into space, asteroids will remain our companions, guides, and perhaps even saviors, whether as resources for exploration, threats to be mitigated, or clues to life's origins. These cosmic boulders continue to captivate and challenge us. And as we look up at the stars tonight, let's remember that the tiny points of light in the sky are not just stars, but also the remnants of a time when planets were just a dream in the making. So, let's keep exploring, learning, and dreaming, because the story of the universe is far from over. And somewhere out there, among the asteroids, the next chapter is waiting to be written. The asteroid belt is a realm of contrasts, ancient, violent, and yet bursting with secrets waiting to be discovered. Millions of unique asteroids populate this mysterious region, each one a time capsule from the solar system's earliest days. Despite its proximity in astronomical terms, humanity has barely begun to explore it. But this is changing. NASA's Dawn mission has embarked on an ambitious journey to unlock the mysteries of the asteroid belt, providing us with the most detailed exploration of this region since its discovery. In July 2011, Dawn reached its first target, Vesta, the second largest asteroid in the belt. Vesta is no ordinary space rock. It is a miniature world, a planet that almost was stunted in its growth by the gravitational dominance of nearby Jupiter. Spanning over 300 miles in diameter, Vesta challenges the misconception that all asteroids are small. In fact, some, like Vesta, are more akin to minor planets, and its surface is home to features that rival Earth's wonders, such as a mountain 3 times taller than Everest. This dwarf planet is like a fossilized snapshot of Earth's infancy, capturing a glimpse of what our planet might have looked like billions of years ago. The data from Dawn revealed that Vesta has a metallic iron core, similar to Earth's. This crucial discovery provides a window into how Earth's own core might have formed during the chaotic early years of the solar system. Vesta, in its embryonic state, tells the story of Earth's beginnings, a time when rocky worlds were just taking shape. Mark Sykes, a co-investigator on the Dawn mission, described the thrill of seeing such a world for the first time, noting how each new discovery reshapes our understanding of the solar system. But Vesta was just the beginning. After studying this stunted world, Dawn ventured deeper into the asteroid belt, setting its sights on Ceres, the largest and most enigmatic object in the belt. 4 times larger than Vesta, and comprising 1/3 of the entire asteroid belt's mass, Ceres is a dwarf planet cloaked in mystery. Its icy surface hints at secrets that may reshape our understanding of how water, and perhaps life, came to Earth. Water is one of Earth's defining features, covering over 2/3 of the planet, yet its origins remain a puzzle. Scientists suspect that asteroids, like icy messengers from the heavens, delivered much of Earth's water billions of years ago. The late heavy bombardment, a period of intense asteroid impacts around 4 billion years ago, transformed Earth into a violent, hellish world. Gigantic asteroids rained down, carving craters, triggering massive earthquakes, and unleashing storms of fire and wind. Yet, amidst this chaos, these asteroids also brought frozen water, which melted upon impact, gradually filling Earth's basins to create oceans, rivers, and glaciers. Ceres, with its icy mantle, offers a unique opportunity to test this theory. This dwarf planet, just 600 miles wide, may hold more frozen water than all of Earth's fresh water combined. If Dawn confirms this, it could provide vital clues about how Earth's lush oceans were formed. Even more intriguing is the possibility of a subsurface ocean beneath Ceres's icy crust. Heat from its core could melt this ice, creating a hidden ocean, an environment that might just support life. The discovery of liquid water on Ceres would be monumental. Life, as we know it, depends on water. If life exists or once existed in the hidden depths of Ceres, it could shed light on how life began on Earth. More broadly, it might suggest that life could arise in similar conditions elsewhere in the universe. Could Ceres, and other icy bodies like it, act as cosmic cradles for life? If so, these ancient worlds could offer not just a glimpse into our past, but also a model for life's potential in the cosmos. The asteroid belt also serves as a graveyard of failed planets, a stark contrast to the thriving ecosystems of Earth. While asteroids like Ceres may have delivered the seeds of life to Earth, others roam the solar system as remnants of destruction. The Moon, for instance, bears the scars of a violent past, its surface marked by countless craters formed during the same late heavy bombardment that shaped Earth. The largest crater on the Moon spans an astonishing 1,500 miles and is further pockmarked by thousands of smaller craters, a stark testament to the relentless asteroid impacts of the early solar system. If the Moon endured such catastrophic impacts, Earth, being larger and more massive, would have faced even greater bombardment. For every visible lunar crater, Earth likely bore 50 or 60 impacts, each one reshaping the planet's surface and influencing its geological and biological evolution. These impacts didn't just carve out massive craters. They brought change, perhaps even opportunity, to a young, volatile Earth. Asteroids, therefore, hold a dual legacy. They are both creators and destroyers. On one hand, they may have delivered the water and organic materials necessary for life. On the other hand, their catastrophic impacts have caused mass extinctions, like the one that wiped out the dinosaurs 66 million years ago. This duality makes asteroids an object of fascination and caution, a reminder of the thin line between creation and destruction. As humanity continues to explore, asteroids remain at the forefront of our quest to understand the cosmos. They are the building blocks of planets, the carriers of life's essentials, and the storytellers of our solar system's chaotic past. Whether as resources for space exploration, harbingers of planetary threats, or potential incubators of life, these ancient rocks continue to shape our understanding of the universe. The story of asteroids is far from over. With every mission, every sample, and every new discovery, we come closer to unlocking the secrets of our cosmic origins. From the asteroid belt to the farthest reaches of the galaxy, these rocky worlds remind us of the infinite possibilities of the universe and the boundless curiosity that drives us to explore it. Asteroids are both creators and destroyers, shaping the universe in profound ways. While they've played a crucial role in forming planets and bringing the building blocks of life to Earth, they also pose a stark threat to life as we know it. Earth, nestled in the vastness of space, is in the direct line of fire, a cosmic shooting gallery where asteroids constantly zip through at incredible speeds. Astronauts have witnessed this danger firsthand. On Apollo 9, an astronaut stepping outside the spacecraft likely encountered a tiny asteroid. Even the smallest space debris moves at thousands of miles per hour, with enough energy to puncture a spacesuit. Thankfully, modern suits are built to withstand these micro-impacts. Still, the Earth itself has a more substantial line of defense: its atmosphere. Most asteroids that enter Earth's atmosphere burn up completely, creating the streaks of light we call shooting stars. These spectacular displays are common. On any given night, you can see dozens of them if you lie under a clear sky. Most shooting stars are no larger than grains of sand, but occasionally, larger rocks make it through. The results can be devastating, as evidenced by Meteor Crater in Arizona. This massive crater, nearly a mile wide, was formed by an asteroid just 150 feet across, smaller than a football field. The impact released energy equivalent to several nuclear bombs, flipping layers of rock upside down and scattering debris for miles. If such an asteroid were to hit a populated area today, it would obliterate an entire city. Yet, this was a relatively small asteroid. The solar system is filled with millions of larger ones, each capable of far greater destruction. Some asteroids, over half a mile wide, are civilization-ending threats. Impacts from such massive bodies have left their mark on Earth throughout history. The most infamous example is the asteroid that struck 66 million years ago, marking the end of the dinosaurs. Evidence of this catastrophic event can be found worldwide, such as the KT boundary in southern Colorado. This thin layer of rock separates the age of dinosaurs from the age of mammals. Below it, fossils of dinosaurs are abundant. Above it, they vanish completely. The KT boundary is rich in iridium, a rare element on Earth but common in asteroids. This layer is the fingerprint of an asteroid impact, a 6-mile-wide rock slamming into Earth, with the force of 5 billion Hiroshima bombs. The asteroid's arrival would have been terrifying. A brilliant, fiery object hurtling through the sky at unimaginable speeds. Upon impact, it unleashed a storm of destruction. The energy released vaporized the asteroid instantly, hurling debris into space and triggering a global firestorm as fragments rained back down. Soot in the KT boundary indicates that wildfires engulfed the planet, consuming forests and releasing immense amounts of carbon into the atmosphere. The skies darkened as a thick layer of dust and soot blocked sunlight, plunging Earth into an impact winter that lasted for years. Temperatures plummeted, and ecosystems collapsed. This chain reaction led to the extinction of 75% of all life on Earth, including the dinosaurs. Such a chilling event underscores the ongoing threat of asteroids. Impacts of this magnitude are rare, occurring roughly every 60 to 100 million years. But smaller, devastating impacts are far more frequent. Statistically, Earth is due for another major collision. The question is not if it will happen, but when. Unlike the dinosaurs, however, humanity has the tools to defend itself, if we act in time. To prevent catastrophe, scientists are constantly monitoring the skies for near-Earth objects, ANEOs, asteroids and comets that come close to Earth's orbit. Advanced telescopes, like the now-retired Arecibo Observatory in Puerto Rico, have been instrumental in tracking these celestial bodies. By analyzing their trajectories, we can predict potential collisions years or even decades in advance. Detecting asteroids is only the first step. The next challenge is figuring out how to stop them. The DART mission, recently conducted by NASA, is a groundbreaking attempt to test asteroid deflection. By deliberately crashing a spacecraft into a small asteroid, scientists proved that it's possible to nudge a threatening asteroid off its collision course with Earth. While this technique works for smaller asteroids detected well in advance, larger threats would require more complex strategies, such as detonating nuclear devices near the asteroid to alter its trajectory. Despite the danger they pose, asteroids are not just threats. They're also opportunities. These ancient rocks hold invaluable scientific information about the solar system's formation and the origins of life. They're also rich in resources, including metals like platinum and rare earth elements, as well as water ice that could support future space exploration. Mining asteroids could one day provide the raw materials needed to sustain human colonies on the Moon, Mars, and beyond. Asteroids even play a role in inspiring the search for extraterrestrial life. Some icy asteroids like Ceres contain water, a key ingredient for life. Missions like OSIRIS-REx and Hayabusa-2 have brought back samples from asteroids, revealing traces of organic compounds. These findings suggest that asteroids may have delivered not only water, but also the building blocks of life to Earth billions of years ago. Could similar processes be happening elsewhere in the universe? If asteroids seeded life on Earth, they might be doing the same in distant solar systems. Many stars are known to host asteroid belts, which could serve as cradles for life in the early stages of planetary development. These belts are cosmic leftovers from planet formation, and their study could unlock secrets about the evolution of other worlds. Asteroids are, in many ways, the universe's storytellers. They narrate the tale of destruction and renewal, chaos and creation. From the fiery birth of planets to the extinction of entire species, these rocky wanderers have shaped the history of the cosmos. And as humanity continues its exploration of space, asteroids remain both a challenge to overcome and a key to understanding our place in the universe. Ultimately, the story of asteroids is the story of life itself. They built our planet, brought water to its parched surface, and may have even delivered the spark of life. But they're also reminders of our vulnerability, a cosmic lottery that could spell the end of civilization as we know it. By studying asteroids, tracking their paths, and preparing for potential impacts, we are not only safeguarding our future, but also deepening our connection to the universe. The next chapter of this story is unfolding now, as missions like DART, Dawn, and OSIRIS-REX continue to explore these ancient objects. With every discovery, we come closer to unlocking the mysteries of the cosmos and ensuring that humanity's future is written among the stars, not erased by a stray asteroid. The vastness of space holds incredible potential, and asteroids may shape humanity's future in ways we are only beginning to understand. These ancient cosmic travelers, once feared as harbingers of destruction, could become our greatest allies in advancing civilization beyond Earth-Tray asteroid. One of the most powerful tools in humanity's arsenal to track asteroids and predict potential threats was the Arecibo Observatory, which, until its decommissioning, served as the world's largest radar dish. Spanning 1,000 feet, it was capable of monitoring near-Earth objects, NEOs, millions of miles away. Unlike traditional telescopes, Arecibo used radar to directly measure an asteroid's distance and trajectory, providing the precision needed to determine if an object was on a collision course with Earthroid. In 2004, astronomers detected a potentially devastating asteroid named Apophis, named after the Egyptian god of destruction. The asteroid, the size of a stadium, sparked widespread concern. Calculations suggested a 1 in 30 chance of a catastrophic impact with Earth on April 13, 2029. A chillingly ironic Friday, the 13th. Such a collision could devastate entire regions, leveling cities and causing global upheaval. Arecibo sprang into action, using its powerful radar to narrow down Apophis's trajectory. The results were reassuring. Apophis would pass extremely close to Earth, closer than the Moon, and even some satellites, but it would not hit. This close call demonstrated humanity's growing capability to track and predict asteroid threats, buying us time to prepare for when, not if, a truly dangerous object heads our way. The challenge now lies in figuring out how to deal with an asteroid that is on a collision course. Blowing it up might seem like an obvious solution, but this could backfire spectacularly. Fragments from the explosion could rain down on Earth, creating multiple impact zones instead of one, potentially increasing the destruction. Instead, scientists focus on deflection strategies, changing the asteroid's speed or trajectory to ensure it misses Earth entirely. One of the most promising techniques involves a gravity tractor. By parking a spacecraft near an asteroid, the gravitational pull between the two objects can subtly alter the asteroid's path. Over time, this small nudge can be enough to avert disaster. The beauty of this method is its precision and minimal risk of creating additional hazards. Another potential solution is using kinetic impactors, essentially slamming a spacecraft into the asteroid at high speed to push it off course. NASA's DART mission, Double Asteroid Redirection Test, successfully tested this concept by altering the orbit of a small asteroid, proving that deflection is not only possible but practical. Such methods give humanity a fighting chance against threats that have loomed since the dawn of our species. Beyond planetary defense, asteroids represent an incredible opportunity. They are treasure troves of valuable resources, containing metals like gold, platinum, and nickel. Mining asteroids could revolutionize industries on Earth and support future space exploration. A single medium-sized asteroid might hold minerals worth trillions of dollars, transforming the economics of space travel and enabling projects that were once the stuff of science fiction. Mining operations in space, however, are no small feat. The cost of launching equipment and returning materials to Earth remains prohibitively high. Yet, there is a way to sidestep this issue, using asteroid resources directly in space. Imagine constructing habitats, spacecraft, or fuel depots in orbit, using materials extracted from nearby asteroids. Colonizing asteroids would eliminate the need to transport massive amounts of supplies from Earth, drastically reducing costs. In many ways, asteroids are like ready-made space stations. Their rocky surfaces can provide natural shielding against radiation and micrometeorites, critical for long-term human habitation. Water trapped in the form of ice on certain asteroids can be harvested and split into hydrogen and oxygen, providing both drinking water and rocket fuel. This capability could pave the way for sustainable space colonies, allowing humanity to expand its presence deeper into the solar system. Looking ahead, the asteroid belt itself could become the foundation of a sprawling interplanetary civilization. This vast region, situated between Mars and Jupiter, contains millions of asteroids, many of which are rich in minerals and other resources. Future settlers could establish cities and factories throughout the belt, transforming it into a hub of human activity. Imagine a network of gleaming cities strung across billions of miles, connected by trade routes, and surrounded by resource-rich asteroids. Factories in space could turn raw materials into spacecraft, habitats, and advanced technologies, all without relying on Earth's dwindling resources. Asteroids also offer an unparalleled opportunity to learn about the origins of our solar system and the building blocks of life. Missions like NASA's OSIRIS-REx and Japan's Hayabusa 2 have already returned samples from asteroids, revealing organic compounds and other clues about the early solar system. These discoveries suggest that asteroids may have played a crucial role in delivering the ingredients for life to Earth. If asteroids seeded life here, they could be doing the same in other solar systems, raising the tantalizing possibility of life elsewhere in the universe. Asteroids have shaped our planet's history in dramatic ways. From the catastrophic impact that ended the age of dinosaurs to the delivery of water and organic molecules that set the stage for life. Now, they offer us a chance to shape our future. Whether as a resource for building spacefaring civilizations or a threat to be mitigated, asteroids hold the key to humanity's next great chapter. Our ability to navigate the challenges and opportunities posed by asteroids will define our place in the cosmos. By advancing our understanding of these ancient objects and developing the technology to utilize and protect ourselves from them, we are taking the first steps toward becoming a truly interplanetary species. The asteroids, once symbols of destruction, may become symbols of hope, a reminder that the universe is vast, full of possibilities, and waiting to be explored. One day, humanity may look back on this era as the beginning of our journey into the stars. As we build cities in the asteroid belt, explore the outer reaches of the solar system, and mine the resources of distant worlds, we will owe our progress to these rocky remnants of creation. They will serve as stepping stones, guiding us toward a future where humanity thrives, not just on Earth, but across the infinite expanse of space. The universe is a place of infinite wonder and mystery, filled with phenomena that push the limits of human understanding. Among these phenomena, black holes stand out as some of the most fascinating and perplexing. They are places where gravity dominates all, so strong that even light cannot escape. These cosmic enigmas challenge everything we know about physics, space, and time. Black holes are not objects in the traditional sense. They are regions of space where matter has been compressed into an incredibly small volume, creating a gravitational pull so immense that it bends and twists the very fabric of space-time. At their heart lies a singularity, a point where density becomes infinite, and the laws of physics, as we understand them, cease to exist. But black holes are more than just extreme gravitational wells. They are also cosmic architects, shaping the galaxies they inhabit. Their immense gravitational influence governs the motion of stars, the formation of planetary systems, and even the distribution of matter across the universe. In a way, black holes are both destroyers and creators, forces of chaos and order intertwined. Take, for example, the supermassive black hole at the center of the galaxy M87. In 2019, astronomers captured the first-ever image of its shadow, revealing a dark void surrounded by a glowing ring of light. This historic image marked a milestone in our ability to study these mysterious entities, giving us a glimpse of the immense power that lies beyond what we can directly observe. Black holes come in many sizes, from the stellar mass black holes formed by collapsing stars to the supermassive giants that anchor entire galaxies. The largest of these can be billions of times the mass of our Sun, with event horizons so vast they could encompass our entire solar system. Yet, despite their size, black holes are remarkably elusive. They emit no light of their own, making them invisible to the naked eye. We can only detect their presence through their interactions with the matter and energy around them. For decades, black holes were considered theoretical constructs, mathematical curiosities predicted by Einstein's theory of general relativity. It wasn't until the mid-20th century that we began to find evidence of their existence. Today, we know they are real, and they are far more complex than we ever imagined. At the core of their mystery lies the event horizon, the point of no return. Anything that crosses this boundary is irreversibly drawn into the black hole, its fate sealed. From the outside, it may appear as though time slows to a standstill at the event horizon, a result of the immense gravitational pull. But for the object itself, the journey is one of complete destruction, as it is stretched and compressed into oblivion. Yet, black holes are not simply engines of destruction. They are also the brightest objects in the universe. The matter that spirals into a black hole forms what is known as an accretion disk, where friction heats the material to millions of degrees, causing it to emit intense radiation. This radiation, particularly in the form of X-rays, allows us to detect and study black holes, even though we cannot see them directly. Black holes also produce relativistic jets, beams of high-energy particles that shoot out from their poles at nearly the speed of light. These jets can extend for millions of light years, shaping their surrounding environments and influencing the formation of stars and galaxies. In some cases, the energy output of these jets rivals that of entire galaxies, making black holes some of the most energetic phenomena in the cosmos. But perhaps the most fascinating aspect of black holes lies in their connection to the fundamental laws of physics. They sit at the crossroads of general relativity, which describes the behavior of gravity on cosmic scales, and quantum mechanics, which governs the behavior of particles on the smallest scales. Studying black holes offers us a unique opportunity to bridge these two theories and explore the nature of reality itself. For example, Stephen Hawking's groundbreaking work in the 1970s revealed that black holes are not completely black. Instead, they emit a faint radiation, now known as Hawking radiation, as a result of quantum effects near the event horizon. This discovery not only changed our understanding of black holes, but also raised profound questions about the nature of information and its preservation in the universe. In this video, we'll take you on a journey to uncover the secrets of black holes. We'll explore how they form, the strange phenomena that occur around them, and their potential role in shaping the fate of the universe. Along the way, we'll delve into the groundbreaking theories that attempt to explain their behavior, from the physics of their formation to the mysteries of their ultimate evaporation. By the end of this journey, you'll see that black holes are more than just objects of fascination. They are windows into the most extreme conditions in the universe, where the known laws of physics are tested to their limits. They teach us about the nature of space, time, and gravity, revealing a universe far stranger and more beautiful than we could ever imagine. So, join us as we embark on this adventure into the unknown, exploring the most enigmatic and powerful forces in the cosmos. This is the story of black holes, where science meets the edge of imagination. To understand the mysteries of black holes, we first need to uncover their origins. Like many cosmic phenomena, their story begins with the stars, the colossal radiant spheres of gas that light up the universe. But even the most massive stars have a finite lifespan, and when they reach their end, they leave behind some of the most fascinating remnants in the cosmos. Stars are essentially massive factories of energy. They are primarily composed of hydrogen, and at their core, a process called nuclear fusion takes place. This is where hydrogen atoms collide under immense pressure and fuse into helium, releasing enormous amounts of energy in the form of heat and light. It is this fusion that powers stars and makes them shine so brightly. But stars are also a delicate balancing act. On one hand, gravity pulls all of their mass inward, trying to compress the star into a smaller and smaller volume. On the other hand, the energy produced by nuclear fusion pushes outward, counteracting gravity's pull. This equilibrium allows a star to remain stable for millions or even billions of years. However, this balance doesn't last forever. Over time, a star begins to exhaust its supply of hydrogen fuel. When this happens, gravity starts to win. The core of the star contracts, and if the star is massive enough, the intense pressure and heat force helium atoms to fuse into heavier elements like carbon, oxygen, and eventually iron. Iron is a pivotal element in the life cycle of a star. Unlike lighter elements, which release energy when they fuse, iron does not. Instead, it absorbs energy, halting the fusion process entirely. This marks the beginning of the end for the star. With no energy pushing outward to counteract gravity, the star collapses in on itself under its own immense weight. What happens next depends on the mass of the star. For smaller stars, this collapse results in a white dwarf, a dense Earth-sized remnant of the star's core. For slightly larger stars, the collapse creates a neutron star, a compact object where a single teaspoon of matter would weigh billions of tons. But for the most massive stars, something even more dramatic occurs. The core of the star collapses so completely that it forms a black hole. All of the star's mass is compressed into an infinitely small and infinitely dense point, known as a singularity. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. This marks the birth of a black hole. The formation of a black hole is often accompanied by one of the most violent events in the universe, a supernova. As the core collapses, the outer layers of the star are blasted outward in a massive explosion. This explosion is so powerful that it briefly outshines entire galaxies, creating elements like gold and uranium in the process, and scattering them across the cosmos. Supernovae play a crucial role in the universe. The elements they produce seed the formation of new stars, planets, and even life itself. In this way, the death of a star gives rise to new beginnings, while the black hole left behind continues to shape its environment in profound ways. But black holes don't all form from collapsing stars. There are different types of black holes, each with its own unique origin story. The most common are stellar black holes, which form when stars much larger than our Sun reach the end of their life cycles. These black holes typically have masses ranging from 3 to 10 times that of the Sun. Then, there are intermediate black holes, which are far larger than stellar black holes but smaller than the supermassive ones found at the centers of galaxies. These black holes are thought to form through the merger of smaller black holes, or the collapse of massive star clusters. Intermediate black holes remain one of the least understood types, as they are much harder to observe. At the top of the scale are supermassive black holes, the giants of the cosmos. These black holes can have masses millions or even billions of times greater than the Sun. They sit at the centers of most galaxies, including our Milky Way, and their origins are still a topic of intense research. Some theories suggest that they grew from smaller black holes over billions of years, while others propose that they formed directly from massive clouds of gas in the early universe. One of the most famous supermassive black holes is Sagittarius A, located at the center of the Milky Way. Despite its relatively small size compared to other supermassive black holes, it has a mass equivalent to about 4 million suns. Sagittarius A star plays a critical role in holding our galaxy together, anchoring the stars in their orbits with its immense gravitational pull. The largest known black hole, TON 618, dwarfs even Sagittarius A. With a mass of approximately 66 billion suns, TON 618 is a true cosmic behemoth. It resides in a distant quasar, a galaxy where a supermassive black hole is actively consuming matter and emitting extraordinary amounts of energy. Observing quasars like this has provided scientists with valuable insights into the growth and behavior of black holes. But black holes are not just remnants of dying stars. Some theories suggest that primordial black holes, tiny black holes formed in the early moments of the universe, could also exist. These black holes would have formed from the collapse of exceptionally dense regions of matter just after the Big Bang. If they do exist, primordial black holes could provide crucial clues about the conditions of the early universe and the nature of dark matter. The study of black holes is still in its infancy, with many questions remaining unanswered. How do supermassive black holes grow so quickly? What role do they play in the evolution of galaxies? And could primordial black holes really hold the key to understanding the mysterious dark matter that makes up most of the universe's mass? What we do know is that black holes are not just the endpoints of stellar evolution. They are dynamic and influential forces in the cosmos. From the death of massive stars to the formation of galactic cores, black holes are deeply intertwined with the story of the universe itself. In the next section, we'll delve into the strange and extreme phenomena that occur around black holes. Phenomena that not only challenge our understanding of physics, but also reveal the immense power and beauty of these cosmic giants. Stay tuned as we continue our journey into the mysteries of black holes. When we imagine a black hole, we often picture an empty void, a dark and mysterious object that consumes everything around it. But surprisingly, the area near a black hole can be one of the brightest regions in the universe. This light and energy come from the accretion disk, a swirling ring of gas, dust, and other matter spiraling into the black hole. The accretion disk forms when matter is pulled toward the black hole's immense gravity. Instead of falling straight in, the matter begins to orbit the black hole, forming a flat, disk-like structure. Within this disk, particles collide and rub against each other at incredible speeds, creating immense friction. This friction heats the material to temperatures of millions of degrees, causing it to glow with intense radiation. The accretion disk is like a cosmic furnace. The material in the disk emits radiation across the electromagnetic spectrum, from visible light to high-energy X-rays and gamma rays. This is why, despite being invisible themselves, black holes can often be detected by the bright light and X-rays emitted from their accretion disks. Accretion disks are not only luminous, but also incredibly efficient at converting matter into energy. When matter falls into the disk and spirals closer to the black hole, gravitational forces and friction convert up to 40% of its mass into energy. To put this into perspective, nuclear fusion, the process that powers our sun, converts less than 1% of mass into energy. This makes the accretion disk one of the most powerful energy sources in the universe. This extraordinary energy output is why quasars, which are powered by supermassive black holes with actively feeding accretion disks, are some of the brightest objects in the cosmos. Quasars can outshine entire galaxies, and their light can travel billions of light-years to reach Earth, giving us a glimpse into the early stages of the universe. The accretion disk is also a dynamic environment where matter behaves in extreme ways. As material spirals inward, it accelerates to incredible speeds, approaching a significant fraction of the speed of light. The closer the material gets to the black hole, the faster it moves, creating stronger friction and generating even more energy. This process not only heats the disk, but also produces powerful electromagnetic fields. These electromagnetic fields are critical for many of the phenomena associated with black holes. For example, they play a role in the formation of relativistic jets, beams of high-energy particles that shoot out from the poles of the black hole. Without the accretion disk, these jets, which can extend millions of light-years into space, would not exist. The structure of the accretion disk itself is influenced by the properties of the black hole. For spinning black holes, the disk can extend closer to the event horizon, where space-time is dragged along by the black hole's rotation in an effect known as frame dragging. The faster the black hole spins, the more compact and energetic the accretion disk becomes. The light emitted by the accretion disk also provides crucial information about the black hole it surrounds. By studying the radiation, scientists can estimate the mass, spin, and growth rate of the black hole. For example, the bright X-rays detected from the disk help pinpoint the black hole's location, while the way light is bent around the black hole reveals its gravitational influence on the surrounding environment. Accretion disks are not just important for studying black holes, they also play a role in shaping their surroundings. As material in the disk heats up and emits radiation, it creates powerful outflows of energy that can influence the formation of stars and galaxies. In some cases, the intense radiation and winds from an accretion disk can push away surrounding gas, limiting star formation in the region. This feedback mechanism is a crucial part of how black holes regulate the growth of galaxies. In the most extreme cases, such as in quasars, the energy released by the accretion disk can heat the intergalactic medium, the vast space between galaxies, affecting the movement and composition of matter on cosmic scales. These interactions show that black holes, far from being isolated phenomena, are deeply connected to the structure and evolution of the universe itself. Despite their brilliance and importance, accretion disks remain a subject of intense study. Their complex dynamics, the role of magnetic fields, and their connection to other black hole phenomena continue to challenge scientists. But one thing is clear. Without the accretion disk, our understanding of black holes and the universe would be incomplete. The accretion disk is not just a byproduct of a black hole's gravity. It is a cosmic powerhouse, a region of intense activity where matter is transformed into light, energy, and radiation. It is through the accretion disk that black holes reveal their immense power and influence, making them not only objects of fascination, but also essential components of the universe's story. From its searing heat to its incredible efficiency, the accretion disk is a true marvel of the cosmos. It is the key to understanding how black holes grow, interact with their surroundings, and shape the universe on the largest scales. In the next section, we'll explore another extraordinary phenomenon surrounding black holes: the relativistic jets that carry their power across millions of light years. Stay tuned. While the accretion disk fuels the brilliance around black holes, another phenomenon takes this energy to extraordinary distances: relativistic jets. These narrow beams of charged particles, traveling at nearly the speed of light, are among the most powerful and far-reaching features of black holes. Stretching millions of light years, relativistic jets are a testament to the immense power black holes can generate. Relativistic jets form in the regions near the black hole, where the accretion disk generates intense magnetic fields. As the black hole spins, the twisting and warping of space-time amplify these magnetic fields, creating a funnel-like structure along the black hole's rotational axis. This funnel channels particles into narrow beams that shoot out from the poles of the black hole. But why do these jets form, and why do they travel so fast? The answer lies in the unique combination of extreme gravity, high-energy particles, and magnetic fields near the black hole. As material in the accretion disk spirals closer to the event horizon, some of it becomes superheated and ionized, creating a plasma of charged particles. These particles interact with the magnetic fields, gaining energy and being accelerated to relativistic speeds, close to the speed of light. Relativistic jets are not only fast, they are incredibly focused. This phenomenon, known as relativistic beaming, occurs because the particles in the jet are moving so quickly that their energy is concentrated into a narrow beam. From certain angles, this concentrated energy appears much brighter than it would otherwise, allowing us to observe jets from enormous distances. One of the most striking examples of relativistic jets can be found in the galaxy M87. Its supermassive black hole produces a jet that extends for over 5,000 light years, visible even from Earth with the help of telescopes like the Hubble Space Telescope. The energy carried by this jet is staggering, capable of heating the interstellar medium and influencing the formation of stars and galaxies around it. The impact of relativistic jets is not limited to their immediate surroundings. These jets play a crucial role in shaping the structure of the universe on a larger scale. As the jets travel through space, they interact with surrounding gas and dust, compressing it and triggering star formation in some regions while suppressing it in others. This dual effect, both constructive and destructive, shows how black holes can regulate the growth and evolution of galaxies. Jets also provide scientists with a unique opportunity to study black holes and their environments. By analyzing the radiation emitted by the jets, Researchers can gather information about the black hole's spin, the strength of its magnetic fields, and the properties of the accretion disk. In some cases, the light emitted by jets is so intense that it outshines the entire galaxy in which the black hole resides, making these phenomena visible from billions of light-years away. But relativistic jets are not just a tool for observation. They also present significant mysteries. For instance, while we understand that magnetic fields are essential for forming and directing these jets, the exact mechanism that sustains them over such vast distances remains unclear. How do these jets maintain their structure and speed over millions of light years? What determines their direction and intensity? These are questions that scientists are still working to answer. One theory suggests that the rotation of the black hole itself plays a key role. Known as the Blandford-Znayak process, this theory proposes that the rotational energy of a spinning black hole is transferred to the jets via magnetic fields. This would explain why the most powerful jets are often associated with rapidly spinning black holes. Relativistic jets are also connected to some of the most energetic and mysterious events in the universe. In gamma-ray bursts, for example, collapsing stars or merging neutron stars can produce jets of such extreme power that they release more energy in a few seconds than the sun will emit over its entire lifetime. These events, while rare, offer a glimpse into the immense forces at play in relativistic jets. Despite their complexity, relativistic jets offer a stunning example of how black holes extend their influence far beyond their event horizons. They are not just isolated phenomena. They are engines of energy and change, capable of shaping the galaxies they inhabit and the universe itself. Relativistic jets showcase the extraordinary power of black holes, carrying energy across cosmic distances and leaving their mark on the universe. They are a reminder that black holes, though invisible, are anything but quiet. In the next section, we'll dive even closer to the heart of a black hole, exploring the strange regions near the event horizon, where space, time, and light behave in ways that defy imagination. Stay tuned. As we approach the black hole itself, the environment grows even stranger. This is where space-time bends and twists under the immense force of gravity, creating phenomena that defy our everyday understanding of the universe. At the center of this extreme environment lies the event horizon, the point of no return. The event horizon is not a physical surface, but rather a boundary. It marks the limit where the escape velocity exceeds the speed of light. Anything that crosses this invisible threshold is lost forever, drawn into the singularity at the black hole's core. Not even light, the fastest thing in the universe, can escape its pull. This is why black holes appear as dark, shadowy voids. From an outside observer's perspective, something curious happens as matter approaches the event horizon. Time appears to slow down. To the observer, the object seems to hover near the boundary, its movement growing slower and slower as it approaches the black hole. But this is an illusion caused by the immense gravitational pull distorting time, a phenomenon predicted by Einstein's theory of general relativity. For the object itself, however, time passes normally as it crosses the event horizon. This stark difference in perspective, known as gravitational time dilation, is one of the many ways black holes reveal the profound effects of gravity on space and time. Just outside the event horizon lies another remarkable region, the photon sphere. This is a narrow zone where gravity is so strong that light itself is forced into orbit around the black hole. In this strange region, photons, the particles of light, travel in circular paths, creating what scientists refer to as the ring of fire. The photon sphere is not only a theoretical concept, it's something we've actually observed. In 2019, the first ever image of a black hole, captured by the Event Horizon Telescope, showed a glowing ring surrounding the dark shadow of the black hole. This ring is light from the photon sphere, bent and twisted by the black hole's gravity. The effects of the photon sphere don't stop there. If you could somehow stand near this region and look outward, you might see light from all directions bending back toward you. In theory, you could even see the back of your own head, as light completes a full orbit around the black hole and returns to your eyes. It's a surreal and mind-bending visualization of how gravity warps space and light. But the strange effects of black holes don't end at the photon sphere. Surrounding a spinning black hole is a region called the ergosphere. This is where the black hole's rotation begins to drag space-time along with it, like a giant cosmic whirlpool. This phenomenon, known as frame dragging, means that within the ergosphere, nothing can remain stationary. Even light is pulled along by the rotation of the black hole. The ergosphere is a region of intense scientific interest, as it opens up the possibility of energy extraction. Through a process known as the Penrose process, it may be possible to extract rotational energy from a spinning black hole. Here's how it works. An object is sent into the ergosphere and splits into two. One part falls into the black hole, while the other escapes with more energy than it started with. This additional energy comes from the black hole's spin, effectively slowing its rotation. While the Penrose process is purely theoretical at this stage, it represents an exciting possibility for utilizing the immense energy of black holes. It also highlights how black holes are not just passive consumers of matter. They are dynamic systems that interact with their environments in complex and surprising ways. While the Penrose process is purely theoretical at this stage, it represents an exciting possibility for utilizing the immense energy of black holes. It also highlights how black holes are not just passive consumers of matter. They are dynamic systems that interact with their environments in complex and surprising ways. They also remind us of the limits of our current knowledge. While we can observe the effects of these regions from a distance, what happens beyond the event horizon remains a mystery. Inside, space-time is compressed into the singularity, where our understanding of physics breaks down. Solving this mystery requires unifying general relativity and quantum mechanics, an achievement that could unlock entirely new realms of science. From the mesmerizing photon sphere to the energy-rich ergosphere and the haunting finality of the event horizon, these regions show just how strange and powerful black holes truly are. They are not just voids in space. They are dynamic, active players in the universe, shaping their surroundings in ways we are only beginning to understand. In the next part, we'll explore how black holes intersect with the world of quantum mechanics, delving into groundbreaking theories like Hawking radiation and the paradoxes that challenge our understanding of information and reality itself. Stay with us as we continue our journey into the heart of black hole mysteries. Black holes are not only marvels of gravity. They are gateways to understanding the quantum world. At the intersection of general relativity and quantum mechanics, black holes present puzzles that challenge our understanding of physics. In this section, we'll explore the groundbreaking discoveries that connect black holes to quantum mechanics and the mysteries they reveal about the nature of reality. One of the most significant breakthroughs in black hole physics came in 1974, when physicist Stephen Hawking made a startling prediction. Black holes are not completely black. Instead, they emit faint radiation, now known as Hawking radiation, as a result of quantum effects near the event horizon. But how is this possible? To understand Hawking radiation, we need to delve into the quantum vacuum, the seemingly empty space that surrounds a black hole. According to quantum mechanics, even the vacuum is not truly empty. It is filled with fluctuating energy, where particle-antiparticle pairs constantly form and annihilate each other in an instant. These fleeting pairs are a manifestation of the Heisenberg uncertainty principle, which governs the quantum realm. Near the event horizon, however, the black hole's immense gravity can separate these pairs before they annihilate. One particle falls into the black hole, while the other escapes into space as Hawking radiation. This escaping particle carries energy away from the black hole, causing it to lose mass over time, a process known as black hole evaporation. Hawking radiation fundamentally changed how we think about black holes. It means that black holes are not eternal, they slowly lose energy and shrink. But this process is incredibly slow. For a black hole with the mass of the Sun, it would take over 10 to the power of 67 years to fully evaporate, far longer than the current age of the universe. Only smaller black holes, such as primordial black holes formed in the early universe, could evaporate within a measurable time frame. As a black hole shrinks, the rate of Hawking radiation increases. In its final moments, the black hole would emit a burst of high-energy radiation before disappearing completely. This theoretical explosion could release immense energy, but detecting such an event would require observing a primordial black hole near the end of its life. A challenge that remains elusive. Hawking radiation also raises profound questions about the nature of information in the universe. In quantum mechanics, information about a system's initial state is never lost. It is always preserved, even if the system changes form. But if a black hole evaporates completely, what happens to the information about the matter it consumed? Does it disappear forever? This conflict between quantum mechanics and general relativity is known as the black hole information paradox, and it is one of the greatest challenges in theoretical physics. If information is lost, it would violate the fundamental principles of quantum mechanics. On the other hand, if information somehow escapes a black hole, it would require a new understanding of how gravity and quantum mechanics interact. One proposed solution is that the information is encoded in the Hawking radiation itself, though the process by which this might occur is not yet understood. Another idea is that the information is stored on the event horizon, in what physicists call the holographic principle. According to this principle, all the information about the three-dimensional interior of a black hole could be encoded on its two-dimensional surface, much like a hologram. The holographic principle is a revolutionary concept in physics. It suggests that the universe itself might work in a similar way to a black hole, with all the information about our three-dimensional reality encoded on a two-dimensional boundary. If true, this principle could provide a new way of understanding the universe, linking black holes to the fabric of space-time on the largest scales. The holographic principle also connects to string theory, a framework that attempts to unify quantum mechanics and general relativity. In string theory, black holes are not singularities, but rather complex structures that can store and process information. While these ideas are still speculative, They offer intriguing possibilities for solving the black hole information paradox and understanding the quantum nature of gravity. Studying black holes directly is extraordinarily difficult. However, scientists have found creative ways to explore the quantum effects predicted by Hawking. In laboratory experiments, researchers create analog systems that mimic the behavior of black holes. For example, sonic black holes use fluids flowing faster than the speed of sound to trap sound waves in a manner similar to how a black hole traps light. These analog experiments have provided promising hints that Hawking radiation is real. By observing these systems, scientists can study the properties of Hawking radiation in controlled environments, offering insights that would otherwise be impossible to obtain. Black holes represent a unique opportunity to bridge the gap between the two pillars of modern physics: general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time, while quantum mechanics focuses on the behavior of particles and fields at the smallest scales. These two theories work remarkably well in their respective domains, but they conflict in the extreme conditions of a black hole's singularity. The singularity, a point of infinite density at the core of a black hole, is where general relativity breaks down. Quantum mechanics suggests that such infinities should not exist. But reconciling the two frameworks has proven to be one of the greatest challenges in physics. A unified theory of quantum gravity could resolve this conflict, providing a deeper understanding of black holes and the fundamental nature of reality. The study of black holes has already reshaped our understanding of physics. Hawking radiation introduced the idea that black holes are not static objects, but dynamic entities that interact with the universe around them. The black hole information paradox has challenged the way we think about information and entropy, inspiring groundbreaking research into the nature of space-time. By pushing the boundaries of what we know, black holes have become testing grounds for new ideas in physics. They challenge us to rethink our assumptions about the universe and explore connections between the largest and smallest scales of reality. Black holes are more than just cosmic mysteries. They are windows into the quantum world. From the faint whisper of Hawking radiation to the profound implications of the information paradox, black holes force us to confront the limits of our understanding. They are the ultimate laboratories for exploring the interplay between gravity and quantum mechanics. In the next section, we'll take a step back to look at the broader role of black holes in the universe. How do they shape the fate of galaxies? And what role might they play in the ultimate destiny of the cosmos? Stay tuned as we continue our journey into the mysteries of black holes. Black holes are not just mysterious objects. They are deeply connected to the grand destiny of the universe. By studying black holes, we gain insight into the long-term fate of galaxies, stars, and even the cosmos itself. In this section, we'll explore the role black holes play in shaping the universe's future and the profound questions they raise about its ultimate end. At the center of most galaxies lies a supermassive black hole. These giants, millions or even billions of times the mass of the Sun, act as anchors, holding their galaxies together. Their immense gravitational pull influences the orbits of stars and the distribution of matter within the galaxy. For example, in our Milky Way, the supermassive black hole known as Sagittarius A plays a crucial role in maintaining the stability of the galactic core. The motion of stars near the center of the galaxy provides clear evidence of its presence and gravitational dominance. But supermassive black holes do more than just hold galaxies together. Through processes like accretion and relativistic jets, they release enormous amounts of energy, which shapes the environment of the galaxy. This energy can heat nearby gas, preventing it from cooling and forming new stars. In this way, black holes regulate star formation, acting as cosmic thermostats that balance the growth of galaxies. Black holes are not passive objects. They actively shape the evolution of galaxies over billions of years. One of the ways they do this is through feedback mechanisms, where the energy they release impacts the surrounding environment. Take quasars, for instance. These supermassive black holes with actively feeding accretion disks can emit radiation and winds so powerful that they push away gas and dust, limiting the galaxy's ability to form new stars. This process, known as quasar feedback, helps explain why some galaxies stop forming stars altogether, transforming from vibrant spiral galaxies into quiet, elliptical ones. On the other hand, black holes can also trigger star formation. When relativistic jets interact with surrounding gas, they compress it, causing it to collapse and form new stars. This dual role, both suppressing and promoting star formation, shows just how influential black holes are in determining the life cycle of galaxies. On larger scales, black holes may hold clues to the ultimate fate of the universe. To understand this, we need to consider the current state of the cosmos. The universe is expanding, with galaxies moving away from each other at an accelerating rate. This expansion is driven by dark energy, a mysterious force that makes up about 68% of the universe. If this expansion continues indefinitely, the universe will enter a state known as the Big Freeze. In this scenario, galaxies will drift so far apart that interactions between them will become rare. Stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will decay, leading to a cold, dark, and lifeless universe. Black holes would be among the last active entities in this future cosmos. As they consume the remaining matter and emit Hawking radiation, they will continue to release energy, albeit faintly. Eventually, however, they too will evaporate, leaving behind only diffuse particles and radiation. While the Big Freeze is the most widely accepted theory, other possibilities exist. In the Big Crunch scenario, the expansion of the universe slows, halts, and reverses. Galaxies would collide, stars would merge, and eventually, everything would collapse back into a singularity, a reversal of the Big Bang. In this scenario, black holes could play a significant role. As galaxies merge, their central black holes would also merge, creating even larger black holes. These massive entities would dominate the universe until the final collapse into a singularity. Another possibility is the Big Rip, where dark energy grows stronger over time, tearing apart galaxies, stars, and even atoms. In this scenario, black holes would not survive either, as the very fabric of space-time would be ripped apart. Each of these scenarios, Big Freeze, Big Crunch, and Big Rip, offers a different vision of the universe's future, but all highlight the central role of black holes in shaping its destiny. To understand the fate of black holes, we must also consider their origins. Some black holes, known as primordial black holes, may have formed shortly after the Big Bang. These tiny black holes, created from dense regions of matter, could provide insights into the conditions of the early universe. Primordial black holes are also intriguing because they could account for some of the universe's dark matter. If they exist, they would be incredibly small and difficult to detect, but their interactions with other matter could leave subtle clues. Studying these black holes could unlock answers to some of the biggest questions in cosmology. Looking to the future, Black holes may not only help us understand the fate of the universe, but also provide practical opportunities for survival. As the universe cools and resources become scarce, advanced civilizations might harness the energy of black holes to sustain themselves. Through processes like the Penrose process or the energy extracted from accretion disks and jets, black holes could serve as powerful energy sources. The immense efficiency of these processes, converting up to 40% of mass into energy, could make black holes essential for interstellar or even intergalactic civilizations. In this way, black holes might not only shape the universe, but also ensure the survival of intelligent life far into the future. Despite decades of research, black holes remain deeply mysterious. From their connection to the fabric of space-time to their role in the universe's destiny, they challenge our understanding of physics and push the boundaries of what we know. They are paradoxical objects, simultaneously destroyers and creators, sources of immense power and ultimate darkness. By studying them, we gain insight not only into the workings of the cosmos, but also into the nature of existence itself. As we look to the future, black holes will continue to be a focal point for scientific exploration. They are not just remnants of stars or anomalies of gravity. They are keys to understanding the deepest questions about the universe's past, present, and future. Black holes hold the secrets to the universe's fate, influencing galaxies, shaping cosmic evolution, and revealing the profound mysteries of space and time. They remind us that the universe is both vast and interconnected, with forces far beyond our comprehension. In the next section, we'll explore how humanity might one day harness the immense power of black holes, unlocking their potential to fuel civilizations and push the boundaries of space exploration. Stay tuned as we continue this journey into the heart of the universe's greatest mysteries. Black holes are often seen as cosmic destroyers, consuming everything that ventures too close. But what if they could also be harnessed as sources of unimaginable power? In this section, we'll explore how humanity might one day utilize black holes to fuel advanced civilizations and unlock the secrets of the universe. Black holes are some of the most efficient energy sources in the universe. As matter falls into a black hole's accretion disk, it heats up to millions of degrees due to friction and compression. This process releases immense amounts of energy, converting up to 40% of the matter's mass into radiation. By comparison, nuclear fusion, the process powering our sun, converts less than 1% of mass into energy. This extraordinary efficiency makes black holes an attractive target for future energy extraction. The light and radiation emitted by the accretion disk alone could power entire civilizations. But how could we capture this energy? One possibility is building a Dyson sphere around a black hole. A Dyson sphere is a theoretical megastructure that surrounds a celestial object to collect its energy. While the concept is often associated with stars, applying it to black holes could be even more effective due to their higher energy output. A Dyson sphere around a black hole would capture the radiation from the accretion disk and convert it into usable power. The energy collected could then be transmitted to habitats or spacecraft, providing a virtually limitless supply of energy. However, building such a structure would require advanced materials and technology far beyond what we currently possess. Alternatively, a simpler design known as a Dyson ring, consisting of a series of smaller, interconnected structures, might be more feasible. These rings could orbit closer to the accretion disk, maximizing energy collection while reducing the challenges of construction. Beyond the accretion disk, another intriguing method for harnessing black hole energy lies in the Penrose process. This theoretical concept involves extracting energy from a spinning black hole's rotational motion. Here's how it works. An object is sent into the ergosphere, the region just outside the event horizon, where space-time itself is dragged along by the black hole's spin. The object splits into two. One part falls into the black hole, while the other escapes with more energy than it originally had. This additional energy is drawn from the black hole's rotation, effectively slowing it down. The Penrose process could, in theory, extract up to 29% of a black hole's rotational energy. While the Penrose process is still theoretical, it offers an exciting glimpse into how black holes could serve as massive energy generators. Advanced civilizations might use this process to fuel spacecraft, power megastructures, or even sustain entire star systems. Relativistic jets, the high-energy beams that shoot out from a black hole's poles, represent another potential energy source. These jets are powered by the intense magnetic fields generated in the accretion disk and can extend millions of light-years into space. Capturing the energy within these jets could provide nearly unlimited power. For example, advanced technologies could use electromagnetic fields to redirect or collect particles from the jets. The energy harvested could then be stored and distributed for various purposes, from powering habitats to driving interstellar travel. However, the immense speed and intensity of relativistic jets would present significant engineering challenges. Black holes might also hold the key to revolutionizing space travel. The immense gravitational forces around a black hole create extreme distortions in space-time, leading to the theoretical possibility of wormholes, shortcuts through space that connect distant regions of the universe. A wormhole, if stable, could allow for faster-than-light travel, making interstellar or even intergalactic exploration feasible. While the idea of using black holes as wormholes is highly speculative, it remains a fascinating possibility. Some scientists suggest that spinning black holes, or Kerr black holes, might create conditions suitable for forming stable wormholes. Harnessing black holes for travel would require not only advanced technology, but also a deeper understanding of the interplay between gravity and quantum mechanics. For now, the idea remains a tantalizing glimpse into what might be possible in the distant future. While the potential of black holes as energy sources and gateways is immense, the practical challenges are equally significant. Building structures near a black hole would require materials capable of withstanding extreme gravitational forces, radiation, and heat. Additionally, the logistics of transporting and storing the energy collected would demand unprecedented advances in engineering and physics. There are also ethical questions to consider. Should humanity exploit black holes, knowing that their energy could alter cosmic environments and potentially affect distant galaxies? How do we ensure that the immense power of black holes is used responsibly rather than for destructive purposes? These questions highlight the need for careful planning and collaboration in any future efforts to harness black hole energy. The concept of using black holes as energy sources aligns with the Kardashev scale, a framework for measuring a civilization's technological advancement based on its energy usage. A Type 2 civilization would harness the energy of its entire star system, while a Type 3 civilization could use the energy of entire galaxies, including black holes. If humanity were to become a Type 2 or Type 3 civilization, black holes would likely play a central role. The ability to harness their energy could provide the resources needed to explore the universe, colonize other star systems, and ensure the long-term survival of intelligent life. Interestingly, the use of black holes as energy sources could also serve as a marker of advanced extraterrestrial civilizations. If an alien civilization were using a black hole, we might detect unusual radiation patterns or artificial structures near the black hole. Observing such activity could provide evidence of intelligent life elsewhere in the universe. This idea aligns with the concept of technosignatures, detectable signs of advanced technology in the cosmos. Searching for technosignatures around black holes could be a promising avenue for future research, offering both scientific and philosophical insights into our place in the universe. As we look to the future, black holes offer both immense opportunities and daunting challenges. They are more than cosmic curiosities. They are potential engines of progress, capable of transforming how we live, travel, and interact with the universe. Whether through Dyson spheres, the Penrose process, or the use of relativistic jets, black holes could provide solutions to some of humanity's most pressing challenges. From energy shortages to the exploration of distant worlds, they remind us of the boundless potential of science and the importance of continuing to push the boundaries of what we know. Black holes, once seen only as symbols of destruction, may one day become humanity's greatest allies in the quest for survival and exploration. They are reminders of the universe's infinite possibilities and the incredible power of human ingenuity. By harnessing the energy and mysteries of black holes, we open the door to a future where the cosmos itself becomes our home. Thank you for joining us on this journey through the mysteries of black holes. From their formation to their potential as engines of creation, they remain some of the most fascinating phenomena in the universe. Until next time, keep exploring, keep questioning, and never stop looking to the stars. As we come to the end of this journey, one thing becomes clear. Black holes are far more than the dark, mysterious voids we once imagined. They are powerful engines of energy, sculptors of galaxies, and windows into the most profound mysteries of the universe. Throughout this exploration, we've uncovered how black holes are formed, from the collapse of massive stars to the creation of supermassive giants at the centers of galaxies. We've ventured into the strange phenomena surrounding them. The glowing accretion disks, the photon spheres bending light, and the relativistic jets stretching across space. We've also explored how black holes connect the worlds of general relativity and quantum mechanics, challenging us to rethink the laws of physics and the nature of reality. From Hawking radiation to the holographic principle, black holes push the boundaries of human understanding in ways no other phenomenon can. Black holes are more than cosmic curiosities. They are key players in the universe's story. They regulate star formation, influence the structure of galaxies, and shape the evolution of the cosmos over billions of years. Their immense gravitational pull holds galaxies together, while their energy output impacts regions of space millions of light years away. But their importance goes beyond their physical effects. Black holes also serve as a testing ground for our most fundamental theories of the universe. They help us probe the relationship between space, time, and gravity, offering clues about the earliest moments after the Big Bang and the ultimate fate of the cosmos. Looking ahead, black holes may hold the key to humanity's future, As we push the boundaries of science and technology, the immense energy potential of black holes could one day power civilizations far more advanced than our own. From harvesting energy via accretion disks to exploring the possibility of wormholes for interstellar travel, black holes inspire us to dream beyond the limits of our current capabilities. They also invite us to consider our place in the universe. If other intelligent civilizations exist, might they already be using black holes to fuel their progress? The search for such technosignatures could lead us to discover that we are not alone, expanding our understanding of life and intelligence in the cosmos. Black holes don't just challenge our science, they challenge our perspective. They remind us of the immense scale of the universe and our small yet meaningful place within it. They show us that the cosmos is both beautiful and terrifying, governed by forces far beyond human control, yet shaped by laws we can strive to understand. They also raise profound questions. What happens beyond the event horizon? Can information ever truly be lost? And what lies at the core of a singularity? These questions inspire both awe and humility, reminding us that the journey of discovery is as important as the answers we seek. Our exploration of black holes is far from over. As telescopes and technologies improve, we'll continue to uncover new insights about these enigmatic objects. From imaging their shadows to detecting gravitational waves from their collisions, every discovery brings us closer to unraveling their secrets. Black holes teach us that the universe is a place of infinite possibility. They show us that even in the darkest regions of space, there is light, energy, and a story waiting to be told. And as we explore these mysteries, we not only learn about the cosmos, we learn about ourselves, our resilience, our curiosity, and our capacity to dream. So, what can we take away from our journey into the heart of black holes? Perhaps it's the realization that the universe is not only vast, but also interconnected. Every star, every galaxy, every black hole is part of a grand cosmic tapestry. And we, as observers and explorers, are an integral part of that story. Black holes challenge us to think bigger, to question the unknown, and to embrace the wonder of the universe. They remind us that while there is so much we have yet to understand, the pursuit of knowledge is itself a beautiful and rewarding endeavor. Thank you for joining us on this journey through the mysteries of black holes. We hope you've been inspired to look deeper into the cosmos, to ask new questions, and to keep exploring the wonders of the universe. Until next time, remember, the universe is vast, its mysteries are endless, and the only limit to discovery is our imagination. The future, stars and Earth. The formation of our Sun marked a pivotal moment in the history of the universe. After 9 billion years of cosmic evolution, countless generations of stars had lived and died, scattering the elements forged in their cores across space. The remnants of one such supernova coalesced into a dense cloud of gas and dust in a relatively quiet region of the Milky Way. Gravity pulled this material together, causing it to heat up and ignite. In a brilliant burst of energy, a star was born, the Sun. Around the newborn Sun, the remaining material formed a protoplanetary disk. This swirling disk of gas and dust contained all the elements needed to create planets, moons, and other celestial bodies. Over millions of years, particles within the disk collided and stuck together, forming larger and larger clumps. These clumps, called planetesimals, eventually grew into the planets of our solar system. Earth, our home, formed in this chaotic environment. Positioned within the Sun's habitable zone, where temperatures allowed liquid water to exist, Earth had the ideal conditions for life. The early Earth was a molten, hostile world, shaped by collisions with other planetesimals and bombarded by asteroids and comets. These impacts played a crucial role, delivering water and organic molecules, essential ingredients for life. As Earth cooled, its surface solidified into a crust, and volcanic activity released gases that formed the atmosphere. Water vapor condensed, creating the first oceans. These early oceans became the cradle of life, where simple, single-celled organisms emerged. Over billions of years, these microorganisms evolved, laying the foundation for the complex ecosystems we see today. While Earth was taking shape, the broader universe continued its cycle of creation and destruction. Supernovae, the explosive deaths of massive stars, remained critical to the chemical enrichment of the cosmos. Without these explosions, elements heavier than iron, such as gold, silver, and uranium, would not exist. Supernovae are nature's most spectacular element factories, capable of forging the heaviest and rarest materials in the universe. Inside the core of a dying massive star, temperatures soar to billions of degrees. Iron atoms, unable to fuse into heavier elements, accumulate in the core, leading to a catastrophic collapse. In a fraction of a second, the core compresses to an unimaginable density. A single cubic centimeter of this matter would weigh as much as all the humans on Earth combined. This rapid collapse generates a shock wave that reverberates outward, smashing through the star's outer layers and restarting the element production line. In these extreme conditions, atoms are fused into new, heavier elements. The debris from the explosion is ejected into space, enriching the surrounding interstellar medium with the building blocks of future stars, planets, and life. These heavy elements eventually find their way into forming solar systems, including our own. The remnants of supernovae, known as nebulae, are among the most beautiful and awe-inspiring structures in the universe. These vast clouds of gas and dust are the raw material for new stars and planets. Images captured by the Hubble Space Telescope reveal intricate details of these cosmic nurseries. The swirling colors and shapes are more than just beautiful. They are evidence of the universe's creativity and dynamism. Within these nebulae, gravity begins to pull material together, forming dense clumps that eventually ignite to become new stars. The leftover material continues to orbit these stars, forming the disks from which planets are born. This cycle of birth, death, and rebirth is what has allowed the universe to evolve into its current state. A vast, complex network of galaxies, stars, and planetary systems. Our Sun, like all stars, is a nuclear furnace. Deep in its core, hydrogen atoms are fused into helium, releasing energy that powers the star and provides light and warmth to the solar system. This process, known as nuclear fusion, has sustained the Sun for 4.6 billion years and will continue to do so for billions more. The Sun's stability and long lifespan have been critical for the development of life on Earth. The Sun also plays a vital role in shaping the solar system. Its gravity holds the planets in orbit, while its energy drives weather patterns and other processes on Earth. Solar winds, streams of charged particles emitted by the Sun, interact with Earth's magnetic field to create phenomena like the aurora borealis or northern lights. These interactions remind us of our intimate connection to the star at the heart of our solar system. Earth's journey from a molten rock to a thriving, life-sustaining planet is a story of resilience and transformation. Early in its history, the planet endured violent impacts that shaped its surface and added to its chemical composition. One such collision, with a Mars-sized object, is believed to have created the Moon, which plays a crucial role in stabilizing Earth's axial tilt and influencing tides. As Earth cooled, its crust solidified and oceans formed. The atmosphere, initially composed of volcanic gases, evolved over time, eventually becoming rich in oxygen due to the activity of photosynthetic microorganisms. These tiny life forms, known as cyanobacteria, were among the first to harness sunlight to produce energy, releasing oxygen as a byproduct. This process, known as photosynthesis, transformed Earth's atmosphere and paved the way for more complex life forms. Every element that makes up Earth, and everything on it, including ourselves, has a cosmic origin. The iron in our blood, the calcium in our bones, and the gold in our jewelry were all forged in the hearts of stars, or during the explosive deaths of supernovae. This realization underscores the profound connection between humanity and the cosmos. As physicist Carl Sagan famously said, "We are made of star stuff." The story of supernova and the elements they create is a reminder of the universe's extraordinary ability to create complexity from chaos. From the simple hydrogen and helium of the early universe to the diverse elements that make up Earth and its inhabitants, the cosmos has been on an incredible journey of transformation. As we look to the future, the legacy of supernovae and star formation continues. New generations of stars are being born in nebulae, and the debris of old stars is enriching the universe with the materials needed for planets and life. Telescopes like the James Webb Space Telescope, JWST, are poised to uncover even more about the processes that shape the universe, from the earliest stars to the formation of habitable worlds. The journey from the Big Bang to the formation of our Sun and Earth is a testament to the power of natural processes. It is a story of cycles, of birth, death, and rebirth, written across the vast canvas of space and time. As we explore the cosmos, we gain not only knowledge, but also a deeper appreciation for the intricate connections that bind us to the universe. From the fiery deaths of massive stars to the quiet formation of a rocky planet in a corner of the Milky Way, the story of the universe is one of endless creativity and wonder. It is a story that continues to unfold, with each discovery bringing us closer to understanding our place in the cosmos. And it is a story that reminds us that, in the grand tapestry of the universe, we are all connected, woven from the same stardust that formed the stars, planets, and galaxies billions of years ago. The universe's future is a tale of extremes, a journey from a vibrant cosmos teeming with energy to a desolate expanse devoid of light and warmth. Saul Perlmutter's discovery of the universe's accelerating expansion reshaped our understanding of its destiny. The culprit behind this acceleration is dark energy, a mysterious force that makes up roughly 68% of the universe. While its nature remains elusive, its effects are undeniable, driving galaxies apart at ever-increasing speeds. Dark energy's influence ensures that the universe will not only continue expanding but will do so at an accelerated pace, leading to a potential end scenario known as the Big Rip. In this bleak vision, dark energy's relentless force will eventually overpower all other forces in the universe. Galaxies will be torn apart, stars will be pulled away from their planets, and even atoms will be shredded into their constituent particles. The universe, once bursting with life and light, will unravel into a cold, featureless void. The timeline for this cosmic disassembly is staggeringly long, measured in trillions of years. But before the ultimate demise, the universe will undergo several transformative phases. 100 billion years from now, the night sky will look dramatically different. The accelerated expansion will push galaxies beyond the observable horizon, making them invisible to any observers still present. The universe will appear lonely and barren, with only a few nearby galaxies remaining visible, those bound to our own Milky Way. As time marches on, the stars will exhaust their nuclear fuel. Stars like our Sun will become white dwarfs, glowing remnants of their former selves. Larger stars will collapse into neutron stars or black holes, while smaller, cooler stars, known as red dwarfs, will slowly fade away. Trillions of years into the future, the cosmos will enter the degenerate era, dominated by these faint, dying remnants. In this era, galaxies will no longer be the vibrant, star-filled structures we see today. Instead, they will be composed of dead or dying stars, their orbits gradually disrupted by gravitational interactions. Over unimaginable spans of time, stars will either be ejected from their galaxies or consumed by central black holes. Even black holes, those enigmatic giants of the cosmos, are not immune to the passage of time. Stephen Hawking theorized that black holes slowly lose mass through a process known as Hawking radiation. Over time, they will emit energy and shrink, eventually evaporating completely. Some are gas giants orbiting dangerously close to their stars, scorched and swollen by extreme radiation. Others are rocky planets shrouded in toxic atmospheres, or frozen in perpetual darkness far from their parent stars. These discoveries have shattered the notion that most planetary systems would mirror our own. Instead, the universe seems to favor chaos and extremes. Consider another example. Kepler 10b, a rocky planet discovered by the Kepler Space Telescope. It is so close to its star that temperatures soar to over 2,500 degrees Fahrenheit, hot enough to melt iron. Its surface, if it exists at all, is likely a molten sea of lava. Kepler 10b is a place of extremes, orbiting its star once every 20 hours. For comparison, Mercury, the closest planet to our Sun, takes 88 days to complete its orbit. Such close proximity to a star is a recipe for destruction, leaving no room for life to take hold. Then there are the so-called hot Jupiters, massive gas giants that defy expectations. Unlike the cool, distant Jupiter in our solar system, these planets orbit perilously close to their stars, where searing temperatures and intense gravitational forces twist and warp their atmospheres. The heat from their stars causes these giants to swell to enormous sizes, their outer layers of gas slowly being stripped away into space. WASP 12b, for instance, is being consumed by its star, leaving behind a trail of gas like the ghost of a comet. While such planets seem utterly alien, each discovery provides valuable insights into the mechanics of planetary systems. They show us the extremes of nature, the outer boundaries of what a planet can endure. And yet, even in these hostile environments, we learn more about the possibilities for planets to exist in stable, life-supporting conditions. The search for a habitable world continues with super-Earths, rocky planets larger than Earth, but smaller than gas giants like Neptune. These planets exist in a tantalizing category, big enough to hold on to thick atmospheres and potentially liquid water, but not so large as to become inhospitable gas worlds. Super-Earths are particularly intriguing because they seem more common than Earth-sized planets, offering a wider canvas for life to emerge. One of the most promising candidates is Proxima Centauri b, a planet orbiting the closest star to our solar system. Located just over 4 light-years away, Proxima Centauri b resides in its star's habitable zone, the region where conditions might allow liquid water to exist. However, its parent star is a red dwarf, prone to violent solar flares that could strip away the planet's atmosphere and make life difficult. Despite this, its proximity makes it an exciting target for future missions that could study its atmosphere and surface. Another intriguing discovery is the TRAPPIST-1 system, home to 7 Earth-sized planets, 3 of which orbit within the habitable zone. This system offers a rare glimpse into a tightly packed planetary neighborhood, where gravitational interactions between planets may play a critical role in their potential to support life. Could one of these worlds be the paradise we seek? Even as we find more planets that seem hostile to life, the search for a second Earth presses on. With tools like the James Webb Space Telescope, capable of analyzing the atmospheres of distant exoplanets, we are on the brink of understanding whether these planets harbor the right conditions for life. Webb's ability to detect signs of water vapor, carbon dioxide, methane, and even oxygen in exoplanet atmospheres will be revolutionary. Such biosignatures could be the first hints of alien life. Our journey is far from over. The universe, vast and brimming with possibilities, holds untold secrets. The more we explore, the more we realize how unique and fragile our own pale blue dot truly is. The search for another Earth is not just a quest to find life elsewhere. It is a reflection of our desire to understand our place in the cosmos. Somewhere out there, a world like ours may exist, orbiting a distant star, waiting to be discovered. For now, we continue to gaze at the heavens, driven by hope, curiosity, and the enduring question: are we alone? The discovery of WASP-12b, a world transformed from a cold gas giant into a blazing inferno, reveals the dramatic forces at play in the cosmos. This planet's journey from the frigid outer reaches of its star system to the fiery embrace of its parent star is a testament to the power of gravity and the chaotic nature of planetary formation. WASP-12b is a galactic pioneer, showing us how the universe can sculpt seemingly impossible worlds. But WASP-12b isn't alone in its fiery fate. Hot Jupiters like it challenge our understanding of how planetary systems form and evolve. These gas giants start far from their stars, in the icy depths where their massive atmospheres can coalesce. Over time, they migrate inward, pulled by the gravitational forces of the swirling disk of gas and dust from which they were born. This inward migration is a slow but inevitable journey, stretching over hundreds of thousands or even millions of years. By the time a planet like WASP-12b reaches its final orbit, it has been utterly transformed. Close to its star, a gas giant faces relentless forces. The heat puffs up its atmosphere, stripping away layers of gas in a process that can eventually destroy the planet altogether. For WASP-12b, this destruction is already underway. Its star is ripping away nearly 190 quadrillion tons of gas every year, creating a glowing tail of material stretching into space. In just 10 million years, a blink in cosmic terms, WASP-12Bi will cease to exist, consumed by its star. What makes WASP-12b even more fascinating is the nature of its core. Beneath its inflated, styrofoam-like atmosphere lies a solid heart rich in carbon. The immense pressures at this depth could compress carbon into exotic forms, potentially creating mountains of diamonds and vast seas of liquid tar. WASP-12b, like so many hot Jupiters, is a world of extremes, a volatile cocktail of fire, gas, and unimaginable pressures. These insights force us to rethink the diversity of planets in the galaxy. WASP-12b is a vivid reminder that not all planetary systems resemble our own. While we marvel at the stability and relative calm of our solar system, it is an outlier in the grand scheme of the universe. The cosmos is full of chaotic, violent, and inhospitable worlds, many of which stretch the boundaries of what we thought possible. Consider the case of Kepler 70b, one of the most extreme planets ever discovered. This rocky world orbits so close to its parent star that it completes a full orbit in just 8 hours. The temperatures on its surface exceed 12,000 degrees Fahrenheit, hotter than some stars. Kepler 70b was once a gas giant, but as its star aged and expanded, the planet was stripped of its outer layers, leaving behind a molten core that continues to bake under the intense heat. It is, quite literally, a planet on fire, a burning ember orbiting a dying star. The discovery of such worlds forces us to confront an unsettling question. How many of these planets were once habitable? Could some of them have started as lush, water-rich worlds before spiraling into the deadly embrace of their stars? The violent forces that shape planets like WASP-12b and Kepler 70b remind us that planetary stability is not guaranteed. Even Earth's orbit could theoretically change under the influence of gravitational interactions over billions of years. Not all migrating planets become hot Jupiters or fiery wastelands. Some are flung entirely out of their star systems. These rogue planets, untethered to any star, drift through the galaxy in perpetual darkness. Without a parent star to provide light and warmth, rogue planets are among the most inhospitable places in the universe. Yet, some scientists speculate that if a rogue planet retains a thick atmosphere or a subsurface ocean, it might still harbor life, warmed by the planet's internal heat. The story of planetary migration extends beyond hot Jupiters and rogue worlds. It also offers clues to the formation of solar systems like our own. In our solar system, gas giants like Jupiter and Saturn likely migrated slightly inward during their formation, shaping the orbits of smaller planets like Earth. Without this delicate balancing act, the stable, life-supporting environment of our planet might never have existed. The process of planetary migration highlights the dynamic nature of the universe. Stars, planets, and moons are not static. They evolve and interact in ways that continually reshape their environments. This dynamism is both a source of destruction and a catalyst for creation. Planets collide, stars explode, and galaxies merge, creating new worlds in their wake. As we continue to search the galaxy for Earth-like planets, the diversity of exoplanets reminds us of the fragility and uniqueness of our own world. For every potential paradise, we find countless hellish landscapes where life as we know it could never survive. Yet, these discoveries fuel our curiosity and expand our understanding of what is possible in the cosmos. WASP-12b and its kin, though inhospitable, serve as cosmic laboratories. They help us understand the forces that shape planets, the extremes of atmospheric chemistry, and the resilience of matter in the face of extreme conditions. Each discovery brings us closer to answering the ultimate question: are we alone? Somewhere in the galaxy, there may be a planet that mirrors our own, a pale blue dot with the right conditions for life. Until we find it, the hellish worlds like WASP-12b remind us of the wonders and challenges of the universe, urging us to continue our exploration of the stars. Korot 7b, a world caught between extremes, reveals the violent and unpredictable nature of the universe. This once massive gas giant, 100 times the size of Earth, has been reduced to a hellish shadow of its former self. Its journey from a cold, gaseous world to a rocky planet of fire and ice is a chilling reminder of the power of gravity and the destructive forces at play in planetary systems. 1.5 billion years ago, Korot 7b began its life far from its star, wrapped in thick layers of gas and ice. Like other gas giants, it formed in the cold outer regions of its star system, where gravity gathered dust and gas into a colossal planet. For millions of years, it remained in this stable, frozen orbit. But then, something changed. A larger, more massive planet began to disrupt the delicate balance of the system, a hot Jupiter moving inexorably toward the star. As the hot Jupiter spiraled inward, its immense gravity began to wreak havoc. Smaller planets were flung into chaotic orbits, and Korot 7b was dragged closer and closer to its star. The once frigid world entered a scorching, unforgiving environment. The heat stripped away its gaseous envelope, layer by layer, until all that remained was its rocky core. What was left behind is a planet of extremes, one that defies the imagination. Today, Korot 7b is locked in a tidal embrace with its star, its rotation synchronized so that one side always faces the heat, while the other is plunged into eternal darkness. The side facing the star is an inferno. Temperatures exceed 4,700 degrees Fahrenheit, hot enough to vaporize rock. The atmosphere, if it can be called that, is a swirling mix of vaporized minerals. Winds carry this molten material to cooler regions, where it condenses into pebbles and rains down, literally a rain of rocks. It's a scene that seems pulled straight from the depths of mythology, a planet where the sky itself burns and solid stone falls like hail. Move to the planet's twilight zone, and the extremes ease slightly. Here, the heat of the star gives way to a narrow band of cooler temperatures. Lava flows cool and solidify into rocky plains. It is a brief respite in an otherwise brutal landscape, but this temperate region is razor thin, a sliver of potential calm surrounded by chaos. Beyond it lies the dark side of the planet. On this far side, the absence of the star's warmth creates a realm of unrelenting cold. Temperatures plummet to hundreds of degrees below zero, freezing everything into an icy stillness. It is a stark contrast to the molten hell of the dayside, yet just as hostile to life. This is a planet of fire and ice, a place where the extremes of temperature make survival impossible. Korot 7b's story is not unique. It is one of many rocky worlds we've discovered, each shaped by violent forces. These planets reveal how far the universe is from the hospitable environments we see on Earth. Rocky exoplanets like 55 Cancri E, for instance, share similarities with Korot 7b. This world, 8 times the mass of Earth, orbits its star at such close range that its year lasts just 18 hours. Its surface is also an inferno, covered in lava flows and scorched by relentless heat. These worlds remind us that Earth is a rare oasis in a universe dominated by extremes. But Corot 7b and its kin are not the only planetary nightmares out there. The chaos wrought by migrating hot Jupiters extends far beyond the planets they drag toward their stars. These massive gas giants also destabilize their star systems, flinging smaller planets into wildly eccentric orbits, or ejecting them entirely into interstellar space. These are the rogue planets, orphan worlds cast adrift between the stars. Rogue planets are enigmatic and haunting. Without a star to orbit, they travel through the darkness of space, illuminated only by distant starlight. On the surface of a rogue planet, the night sky would be unchanging and eerily silent. There would be no sunrise or sunset, no warmth to sustain life. These planets, severed from their parent stars, are relics of violent gravitational battles. Some were gas giants like Corot 7b, while others might be rocky worlds, frozen Earth-like planets cast into perpetual night. What makes rogue planets even more astonishing is their sheer number. Some estimates suggest that these orphan worlds may outnumber stars in the galaxy. If true, it would mean hundreds of billions of planets roam the void between the stars, their stories lost to the darkness. Despite their isolation, rogue planets may still hold secrets. If a rocky rogue planet retains a thick atmosphere or subsurface ocean, it could generate heat through radioactive decay or tidal forces. In such cases, even these dark, frozen worlds could harbor life in some form. A tantalizing possibility that challenges our understanding of what makes a planet habitable. The story of Corot 7b, rogue planets, and hot Jupiters underscores the unpredictability of planetary formation and evolution. While we search for Earth-like worlds, the reality is that most planets are profoundly different from our own. They are shaped by chaos and violence, molded by forces that destroy as much as they create. Yet, these discoveries also remind us of Earth's uniqueness. In a galaxy filled with planets of fire and ice, rogue wanderers and searing giants, our pale blue dot remains a rare and fragile gem. The search for other worlds continues, but each step reveals just how extraordinary our own world truly is. As we gaze out into the cosmos, these planets from hell inspire awe and caution. They show us the extremes of the universe and remind us of the delicate balance that makes Earth so special. Somewhere, perhaps, another world like ours may exist, a haven of life in an otherwise hostile galaxy. Until we find it, we will continue to explore, learn, and marvel at the diversity of the universe. The discoveries made by NASA's Kepler Space Telescope have revolutionized our understanding of the cosmos. Kepler has revealed a galaxy teeming with planets, planets of all sizes, compositions, and orbital paths. Among them, some are fiery infernos, others frozen wastelands, and a select few hold the tantalizing promise of being just right. This sheer abundance of planets is both humbling and hopeful. While most of the worlds we've found are utterly inhospitable, their sheer number suggests that habitable planets like Earth might not be as rare as they seem. The key to finding another Earth lies in identifying planets located within the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist. Water is fundamental to life as we know it, acting as the universal solvent where complex chemistry can flourish. Without water, there can be no oceans, no rivers, no rain, and likely no life. As astronomers often say, follow the water. It's the guiding principle for our search. Kepler allows us to pinpoint a planet's distance from its star, a critical factor in determining habitability. Too close, and water boils away into vapor, leaving behind barren deserts. Too far, and water freezes into perpetual ice, locking a planet in a frozen state. Earth exists in the sweet spot, a precarious balance that has allowed life to thrive. Finding planets with a similar balance is the ultimate goal of planet hunters. But the search has been anything but straightforward. Kepler has identified thousands of planetary candidates, but few lie within their star's habitable zone. And none so far have been confirmed as true Earth twins. Instead, we've uncovered a kaleidoscope of alien worlds that push the boundaries of what planets can be. Corot 7b, with its rain of molten rock, and pulsar planets, bombarded by deadly radiation, are stark reminders of the universe's extremes. These are worlds where the concept of life seems impossible, where even the barest conditions for survival are absent. Yet, the sheer number of planets we've found is reason for optimism. Planets, it seems, are easy to make. The galaxy is brimming with them. 50 billion by some estimates, with many orbiting stars like our Sun. If planets are so abundant, then even the rarest ones, those that resemble Earth, could exist in significant numbers. Statistically, there must be other planets out there with conditions similar to ours. Consider the potential implications. Even if only 1% of planets are in the Goldilocks zone, that could still mean 500 million potentially habitable planets in the Milky Way alone. The vastness of these numbers inspires hope, even as it challenges our imagination. Among the countless stars and their orbiting planets, there may be dozens, hundreds, or even thousands of Earth-like worlds waiting to be discovered. Kepler's discoveries have also deepened our appreciation for Earth's uniqueness. Our planet is not only in the perfect location relative to the Sun, but it also benefits from a host of other factors that make life possible. Its magnetic field shields us from harmful radiation, its atmosphere retains heat and provides oxygen, and its stable climate supports diverse ecosystems. Together, these factors create a delicate balance that might be exceedingly rare in the cosmos. As we continue to search for Earth's twin, new technologies promise to bring us closer to an answer. The James Webb Space Telescope, for example, is designed to analyze the atmospheres of distant exoplanets, searching for signs of habitability or even life. By detecting the presence of water vapor, oxygen, methane, and other biosignatures, Webb could provide the first concrete evidence of planets capable of supporting life. Even beyond James Webb, upcoming missions like TESS, Transiting Exoplanet Survey Satellite, and the European Space Agency's PLATO mission are expected to expand our catalog of exoplanets. With each new discovery, we refine our understanding of where and how to look for habitable worlds. These tools bring us closer to answering the age-old question: are we alone? The search for exoplanets is not just about finding life elsewhere. It's about understanding our place in the universe. Each new planet we discover, whether a fiery gas giant or a frozen rogue world, adds to our knowledge of how planetary systems form and evolve. They remind us of the diversity of the cosmos and the fragile conditions that make Earth so special. Despite the challenges, the search continues with undiminished fervor. For every planet from hell we uncover, we gain insights into the mechanisms that create and sustain planets. For every failed attempt to find an Earth twin, we are reminded of the vast possibilities that lie ahead. Somewhere in the galaxy, orbiting a distant star, there may be a pale blue dot just like ours. A world teeming with life, oceans, and skies, waiting to be found. Until that day comes, our journey among the stars serves as a testament to humanity's curiosity and determination to explore the unknown. Kepler has opened our eyes to a universe full of planets. It has shown us the extremes, the inhospitable, and the breathtakingly alien. But it has also given us hope, a belief that among the billions of planets in our galaxy, there are worlds that could be home to life. Worlds that might one day answer the profound question, are we alone? Hubble's discovery was revolutionary, but it also raised profound questions. If the universe had a beginning, what triggered it? What existed before the universe began? These questions have intrigued and challenged scientists for nearly a century, driving deeper exploration into the origins of everything we see today. To understand the birth of the cosmos is to understand the origins of ourselves. Instead, the universe was filled with fundamental particles like quarks and gluons, zipping around in chaotic motion. These particles were the building blocks of the atoms that would eventually make up stars, planets, and life itself. But first, the universe had to cool. As the universe expanded, it began to cool down. Within minutes of the Big Bang, quarks combined to form protons and neutrons, creating the nuclei of the first atoms, mostly hydrogen and helium. These two elements are the simplest and most abundant in the universe, and they remain its primary constituents even today. The next step in the cosmic story would take hundreds of millions of years. As the universe continued to cool and expand, gravity began to take hold. Hydrogen and helium gas clouds coalesced under the pull of gravity, forming the first stars. These stars were massive, burning their fuel at extraordinary rates and exploding as supernovae after just a few million years. These violent explosions seeded the universe with heavier elements like carbon, oxygen, and iron, the building blocks of planets, life, and everything we see around us. Stars, it turns out, are the universe's factories. Inside their cores, nuclear fusion forges heavier elements from lighter ones. For instance, hydrogen atoms combine to form helium. And in larger stars, helium atoms fuse to create carbon, oxygen, and eventually iron. When these stars die, they scatter these elements into space, enriching the universe with the raw materials for new stars, planets, and eventually life. Physicist Lawrence Krauss explains it best. We are truly stardust. The atoms in our bodies were forged in the cores of stars that lived and died billions of years ago. Every breath we take, every step we make, connects us to the cosmos in the most profound way. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was born in the hearts of stars that lived and died long before our sun ever existed. The formation of the first galaxies was the next major milestone in the universe's evolution. Over hundreds of millions of years, gravity pulled clumps of stars together, creating swirling islands of light, galaxies. These vast star cities are the building blocks of the cosmos, each containing billions or even trillions of stars. Galaxies, like stars, come in many shapes and sizes. Some are elegant spirals, like our own Milky Way, while others are chaotic and irregular, shaped by collisions and interactions with neighboring galaxies. The formation of our solar system occurred much later, about 4.6 billion years ago. It began with a massive cloud of gas and dust, which collapsed under gravity to form a new star, our Sun. Around the Sun, smaller clumps of material collided and merged, forming the planets, moons, asteroids, and comets we see today. Earth, our home, was one of these rocky worlds, forming in the Sun's habitable zone, where conditions were just right for liquid water to exist. The young Earth was a fiery, hostile place, bombarded by asteroids and volcanic eruptions. Yet, from this chaos emerged the conditions necessary for life. Over billions of years, the planet cooled, oceans formed, and primitive life took hold. From simple microorganisms, life on Earth evolved into the incredible diversity we see today, a process spanning billions of years and shaped by countless cosmic events. Understanding the universe's origins also helps us glimpse its ultimate fate. The universe is still expanding, as Hubble first observed, and this expansion is accelerating. The mysterious force driving this acceleration is known as dark energy, a phenomenon that remains one of the greatest mysteries in modern physics. If the expansion continues unchecked, the universe may eventually face a big freeze, where galaxies drift so far apart that stars burn out, leaving the cosmos dark and cold. Yet, there is beauty in this cosmic cycle. The atoms that make up our bodies, our planet, and our universe will continue to exist, perhaps to form new stars, new planets, and even new life billions of years from now. As Krauss eloquently states, we are not only stardust, we are part of the universe's story. The discovery of exoplanets, galaxies, and the cosmic forces that shape them reminds us of our interconnectedness with the cosmos. Every step we take, every breath we draw, ties us to a universe that has been evolving for billions of years. As we search for another Earth, we are also seeking a deeper understanding of ourselves and our place in this vast and mysterious cosmos. Perhaps one day, we will find a pale blue dot orbiting a distant star, a world that mirrors our own. Until then, the story of the universe continues to unfold, reminding us of the incredible journey that brought us here and the infinite possibilities that lie ahead. As the universe cooled further, something remarkable occurred. The electrons, now moving at slower speeds, were able to combine with protons and neutrons to form the first stable atoms. This epoch is known as recombination, a pivotal moment in the history of the cosmos. For the first time, the universe became transparent, allowing light to travel freely through space. The photons released during this period make up what we now detect as the cosmic microwave background radiation (MBR), a faint glow that permeates the entire universe and serves as a snapshot of the cosmos in its infancy. The CMBR is the oldest light in the universe, a relic from when it was just 380,000 years old. When we study it today, using powerful telescopes like the Planck satellite, we are essentially looking back in time. Tiny fluctuations in the CMBR provide clues about the distribution of matter in the early universe, offering a glimpse into the seeds of galaxies and large-scale cosmic structures. These fluctuations were incredibly small, variations in temperature of only a few millionths of a degree, but they held the key to the formation of everything we see today. Over the next few 100 million years, the universe continued to expand and cool. Hydrogen and helium, the two simplest and most abundant elements, dominated this era, often referred to as the cosmic dark ages. There were no stars, no galaxies, and no light. Only vast clouds of gas spread thinly across an expanding universe. But within this darkness, gravity was quietly at work. Gravity began pulling the densest regions of gas together, forming clumps that grew larger and more massive over time. These clumps eventually became the first stars, marking the end of the cosmic dark ages and the dawn of a new era of light. These early stars, called population 3 stars, were unlike the stars we see today. They were enormous, hundreds of times the mass of our Sun, and burned at incredibly high temperatures. Because they formed from primordial hydrogen and helium, they lacked the heavier elements that give modern stars their complexity. These massive stars lived fast and died young, burning through their fuel in just a few million years before exploding as supernovae. These explosions released enormous amounts of energy, creating the first heavy elements like carbon, oxygen, and iron. The death of the first stars seeded the universe with these essential elements, enabling the formation of more complex stars, planets, and eventually life. As the universe evolved, galaxies began to form. These immense structures, composed of billions or even trillions of stars, became the building blocks of the cosmos. Galaxies themselves grouped into clusters and superclusters, connected by vast filaments of dark matter that form the cosmic web. A sprawling, interconnected structure that defines the large-scale shape of the universe. The Milky Way, our home galaxy, formed during this period of cosmic construction. Over billions of years, it grew by merging with smaller galaxies and accumulating gas and dust. In its center lies a supermassive black hole, millions of times the mass of the Sun, which influences the movement of stars and gas throughout the galaxy. Surrounding the Milky Way are countless stars, planets, and moons, along with mysterious dark matter that makes up most of the galaxy's mass, yet remains invisible and undetectable except through its gravitational effects. Within one of the Milky Way's spiral arms, about 4.6 billion years ago, our solar system began to take shape. It started as a dense cloud of gas and dust, which collapsed under gravity to form a spinning disk. At the center of this disk, a new star ignited, our Sun. Around it, smaller clumps of material collided and stuck together, forming the planets, moons, asteroids, and comets that make up the solar system today. Earth, our home, was one of these planets, forming in the Sun's habitable zone, the region where temperatures are just right for liquid water to exist. In its early years, Earth was a chaotic, molten world, bombarded by asteroids and comets. These impacts not only shaped the planet's surface, but also delivered water and organic molecules, setting the stage for life. The formation of Earth's atmosphere and oceans marked the beginning of a profound transformation. Simple, single-celled organisms appeared, harnessing energy from sunlight and chemical reactions to survive. Over billions of years, these microorganisms evolved into more complex life forms, eventually giving rise to plants, animals, and, much later, humans. As life flourished on Earth, the universe continued its slow march forward. Stars lived and died, galaxies collided and merged, and the expansion of the universe accelerated. This acceleration, driven by the mysterious force known as dark energy, remains one of the greatest puzzles in cosmology. Dark energy is believed to make up about 68% of the universe, with dark matter accounting for another 27%, leaving only 5% for the ordinary matter that makes up stars, planets, and everything we can see. Today, the universe is 13.8 billion years old and filled with wonders. From the vast beauty of the Milky Way to the distant galaxies billions of light years away, it is a testament to the power of natural processes. Every atom, every star, every galaxy is a product of cosmic evolution. A story that began with the Big Bang and continues to unfold. And yet, the story is far from over. The universe's ultimate fate remains uncertain. If dark energy continues to drive the expansion of space, galaxies will drift farther apart until the universe becomes a cold, dark, and empty place. A scenario known as the Big Freeze. Alternatively, if dark energy behaves differently than we expect, the universe could eventually collapse in a big crunch, reversing its expansion. Or perhaps dark energy could rip the cosmos apart in a dramatic Big Rip. Despite these uncertainties, one thing is clear. The universe is a place of constant change, driven by forces we are only beginning to understand. From its fiery beginnings to the formation of stars, galaxies, and life, the cosmos is a story of transformation, resilience, and discovery. As we gaze at the stars and study the faint echoes of the Big Bang, we are reminded of our deep connection to the universe. We are stardust, shaped by the same processes that created the galaxies and fueled the first stars. Our atoms, forged in the hearts of dying stars, are a testament to the remarkable journey that began billions of years ago. The universe's story is our story, written across the vast canvas of space and time. As we continue to explore, we uncover new chapters, each more extraordinary than the last. And with every discovery, we gain a deeper understanding of where we come from, where we are, and where we might be headed. A journey that will forever unite us with the cosmos. As the baby universe expanded and cooled, the tiny cracks in its otherwise uniform structure became crucial to its evolution. These imperfections, detected in the cosmic microwave background radiation, CMBR, by missions like WMAP, were the seeds of everything we see today. Galaxies, stars, planets, and even life itself. Without these small fluctuations in density, the universe would have remained a dull expanse of gas, devoid of the intricate structures that define it now. The material within these cracks was composed of swirling clouds of hydrogen and helium, the simplest and most abundant elements in the universe. Gravity began to work its magic, pulling the denser regions together. Over time, these regions grew more massive, attracting more gas and forming vast clumps. The voids between these clumps expanded, creating the cosmic web, a sprawling network of filaments connecting galaxies across billions of light years. These filaments, first glimpsed through simulations and later observed directly, reveal the large-scale structure of the universe, a breathtaking tapestry shaped by gravity. The next transformative moment in the universe's history came with the formation of the first stars. About 200 million years after the Big Bang, these dense clumps of gas reached critical mass. Gravity compressed them to the point where nuclear fusion ignited in their cores, creating the first sources of light since the CMBR. These early stars, known as population 3 stars, were unlike any stars we see today. They were massive, burning their fuel quickly and intensely, with lifespans of just a few million years. Composed almost entirely of hydrogen and helium, they lacked the heavier elements that make up modern stars. When these primordial stars died, they exploded as supernovae, scattering their enriched material across space. These supernovae created heavier elements like carbon, oxygen, and iron, the building blocks of planets, life, and even human bodies. Each supernova was like a cosmic alchemist, transforming the simplest elements into the complex ingredients necessary for the universe's next chapters. As the universe grew older, these enriched materials gave rise to the next generations of stars, which included more elements in their formation. Over billions of years, stars grouped into galaxies, and galaxies formed clusters, connected by the filaments of the cosmic web. One of these galaxies was the Milky Way, which would eventually become home to our solar system. The Milky Way itself formed through a process of mergers and accretion. Smaller galaxies collided and combined, their stars and gas clouds melding into a growing spiral structure. In its center, a supermassive black hole emerged, exerting a gravitational influence that shaped the galaxy's evolution. Surrounding it, billions of stars, along with planets, asteroids, and comets, formed a cosmic ecosystem. Among these stars was our Sun, which ignited around 4.6 billion years ago. The Sun was born from a dense cloud of gas and dust, part of a vast molecular cloud in one of the Milky Way's spiral arms. As the cloud collapsed under gravity, it spun faster, forming a disk around the young star. Within this protoplanetary disk, small particles of dust and ice collided and stuck together, gradually growing into planetesimals, early building blocks of planets. Over millions of years, these planetesimals coalesced into the planets, moons, and other objects that make up our solar system. Earth, the third planet from the Sun, formed within the Sun's habitable zone, where conditions allowed liquid water to exist. In its early years, Earth was a violent, molten world, bombarded by asteroids and comets. These impacts not only shaped the planet's surface, but also delivered water and organic molecules, the essential ingredients for life. As Earth cooled, its surface solidified, forming a thin crust. Volcanic activity released gases that created an atmosphere, and water vapor condensed to form oceans. These early oceans became the cradle of life. Simple microorganisms emerged, harnessing energy from sunlight and chemical reactions. Over billions of years, these tiny organisms evolved into more complex forms, eventually giving rise to plants, animals, and, much later, humans. While life flourished on Earth, the universe continued its slow march forward. Galaxies collided and merged. Stars lived and died. And new stars were born from the remnants of older ones. The expansion of the universe, driven by the mysterious force known as dark energy, accelerated. Dark energy, which makes up about 68% of the universe, remains one of the greatest enigmas in modern physics. Its influence ensures that galaxies are moving away from each other at an ever-increasing pace. The discovery of dark energy added a new layer of complexity to our understanding of the universe's fate. If its effects continue unabated, the universe could face a big freeze, where galaxies drift so far apart that stars exhaust their fuel, leaving the cosmos cold, dark, and lifeless. Alternatively, dark energy could trigger a big rip, tearing apart galaxies, stars, and even atoms. These scenarios remind us of the universe's impermanence and the delicate balance that sustains it. Despite these cosmic challenges, the story of the universe is one of resilience and creativity. From the tiniest quantum fluctuations in the CMBR to the majestic galaxies that fill the night sky, every aspect of the cosmos is a testament to the power of natural processes. The imperfections in the early universe, detected by missions like WMAP and later confirmed by the Planck satellite, show us how these processes unfolded. The Planck satellite, launched in 2009, provided the most detailed map of the CMBR to date. By analyzing this ancient light, scientists gained unprecedented insights into the universe's age, composition, and structure. Planck revealed that the universe is 13.8 billion years old, composed primarily of dark energy, dark matter, and ordinary matter. It confirmed that the tiny cracks in the early universe became the galaxies, clusters, and superclusters we see today. One of the most profound implications of these discoveries is our connection to the cosmos. The hydrogen in our water, the calcium in our bones, and the iron in our blood were all forged in the cores of stars or during the explosive deaths of supernovae. As physicist Lawrence Krauss famously said, "We are stardust." This realization underscores the intimate relationship between humanity and the universe. Our journey to understand the universe is far from over. Telescopes like the James Webb Space Telescope promise to unveil new secrets about the first galaxies and stars, while projects like the Euclid mission aim to unravel the mysteries of dark energy and dark matter. As we peer deeper into space and time, we uncover new chapters in the cosmic story. From the faint glow of the CMBR to the brilliant light of distant galaxies, the universe is a constant source of wonder. Its story, spanning billions of years, is a tale of creation, destruction, and renewal. A journey from simplicity to complexity, from chaos to order. As we explore the cosmos, we not only learn about the universe's origins, but also gain insight into our own place within it. The universe began as a tiny, hot fireball, a moment of pure energy. From that singular event emerged everything we see today: galaxies, stars, planets, and life. And as we look to the future, we carry with us the knowledge that we are part of this vast and extraordinary story. A story that continues to unfold, connecting us to the cosmos in ways we are only beginning to understand. Hubble's discoveries redefined our understanding of the universe. The Hubble Deep Field Image was more than a snapshot. It was a time machine, revealing galaxies from a billion years after the Big Bang. These faint smudges of light told a story of transformation, of stars creating the heavier elements that would eventually become the building blocks of planets, life, and everything we see today. By analyzing the spectra of these distant galaxies, scientists confirmed that the early universe had already started producing elements beyond hydrogen and helium. These included carbon, oxygen, and nitrogen, essential ingredients for life. This confirmed Fred Hoyle's groundbreaking theory that stars acted as cosmic forges, creating heavier elements through nuclear fusion. Hoyle's idea of stars as factories of matter became a cornerstone of modern astrophysics. The process begins deep within a star's core. Under immense pressure and heat, hydrogen atoms fuse to form helium, releasing vast amounts of energy, a process that powers stars like our Sun. As the star ages and its core temperature increases, helium fuses into heavier elements like carbon and oxygen. In the most massive stars, this chain of fusion reactions continues, creating elements as heavy as iron. But iron marks the end of the road. Fusion can no longer provide the energy needed to counteract gravity, and the star collapses. For the most massive stars, this collapse triggers a supernova, a violent explosion that scatters the star's material across the cosmos. It is during these explosions that even heavier elements like gold, platinum, and uranium are formed. Every atom of gold in your jewelry and every molecule of oxygen you breathe was forged in the heart of a dying star. These stellar explosions seeded the universe with the elements necessary for the formation of new stars, planets, and eventually, life. The material ejected by one generation of stars becomes the raw material for the next. This cycle of creation and destruction continues to shape the universe, making it richer and more complex with each iteration. Hubble's images of star-forming regions, like the pillars of creation in the Eagle Nebula, captured this process in breathtaking detail. These towering columns of gas and dust are interstellar nurseries, where gravity pulls material together to form new stars. Within these dense regions, stars ignite and begin their nuclear fusion, lighting up the nebula with their brilliance. These newly born stars, in turn, shape their surroundings, blowing away gas and dust with powerful stellar winds and creating space for the next generation of stars. In some cases, the leftover material around a newly formed star condenses into disks where planets take shape. This process mirrors the formation of our own solar system, where a protoplanetary disk surrounding the young Sun gave birth to Earth and its neighboring planets. Hubble's ability to peer into these nurseries offers us a glimpse of how planetary systems like ours come into existence. The successes of the Hubble Space Telescope were hard-earned, but its legacy is unparalleled. Its images transformed our understanding of the cosmos, not just by showing us where we came from, but by inspiring questions about what lies beyond. Hubble's observations paved the way for the next generation of telescopes, such as the James Webb Space Telescope, JWST, launched in 2021. JWST builds on Hubble's legacy by pushing the boundaries even further. With its powerful infrared capabilities, it can peer through dense clouds of gas and dust to study the earliest galaxies and star-forming regions in unprecedented detail. Where Hubble saw the first galaxies, JWST aims to see the very first stars, shedding light on the universe's darkest epochs. It will also search for signs of life on exoplanets by analyzing their atmospheres for chemical fingerprints of water, oxygen, and other molecules associated with life. Hubble's revelations, combined with data from missions like JWST, remind us that the universe is a place of constant change and creativity. Every image, from the pillars of creation to the Hubble Deep Field, tells a story of how the cosmos evolves over billions of years. The light captured by these telescopes allows us to witness events that happened long before Earth even existed. But these discoveries also raise profound questions. Are we alone? Is there another world out there, orbiting a distant star, where life has taken root? Hubble's observations of exoplanets and JWST's ability to analyze their atmospheres bring us closer to answering these questions. By studying how stars create the elements needed for life and how planets form in their wake, we gain insight into the conditions that might make life possible elsewhere. As we look at the spectacular images captured by Hubble, it's impossible not to feel a sense of wonder. The stars, galaxies, and nebulae it reveals are not just distant objects. They are part of our story. The atoms in our bodies were forged in the fiery cores of stars. The water we drink contains hydrogen created in the Big Bang. Even the gold in our jewelry came from the cataclysmic deaths of ancient stars. Fred Hoyle's insight into stellar nucleosynthesis and Hubble's exploration of the cosmos have deepened our understanding of this connection. They remind us that we are not separate from the universe, but an integral part of it. We are made of star stuff, shaped by the same processes that govern the galaxies and nebulae we see in Hubble's images. The discoveries of the Hubble Space Telescope mark a milestone in humanity's journey to understand the cosmos. But they are not the end of the story. With JWST and other next-generation telescopes, we are poised to uncover even more about the universe's origins, evolution, and future. From the first stars to the birth of new worlds, the universe is a story of transformation, a story we are privileged to witness. As we continue to explore, we are reminded of the words of Carl Sagan: "We are a way for the cosmos to know itself." Through the lens of telescopes like Hubble, we glimpse the vastness of the universe and our place within it. And with every new discovery, we take another step in understanding the profound connection between ourselves and the stars. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.